Welcome to the continuation of the 2023 NASA STEM Enhancement in Earth and Space Science High School Internship Science Symposium. SEAS is a collaboration between NASA and the University of Texas Center for Space Research. Former SEAS interns have gone on to major in STEM in college, interned at NASA centers and space contractors, and been hired by NASA working on missions such as Europa. We are excited to learn about the future accomplishments of the interns of 2023. This year, we received almost 2,000 complete applications and selected 200 students in 10th and 11th grades as participants who were assigned to 18 different Earth and space science projects. Research was conducted in Earth and space science, environmental studies, climate research, mission design, and technology. To say these students are amazing is an understatement. Each student conducted 60 to 90 hours of research in Earth and space science, Python coding, and project-specific work prior to starting their project. Interns heard from 10 NASA subject matter experts that highlighted NASA missions, opportunities, and careers during the course of this internship as part of the NASA SEAS Speaker Series. You are in for a treat as you hear from these amazing young people, our scientists and engineers of the future. On behalf of Selena Miller and myself, Margaret Baggio, the managers of the SEAS program, welcome to NASA SEAS 2023. Today, we will have 16 teams and individual project video presentations. We will divide the afternoon into 2 sessions with one 20-minute break at 3:15 Central Time. Project video presentations will either be 5, 10, or 20 minutes in length, followed by questions and answers. Please post your questions on the slido.com website and use the code SEAS23. Here is our schedule for the day. We will have presentations by teams followed by a 5 or 10-minute Q&A. We will invite each team presenting to turn on their cameras and mics to answer the questions posed by those that are listening. During the 20-minute break, we invite you to watch highlights of the student intern produced products as part of the Earth and Space Science and Python coding projects. Our first presentation are from the Measuring Environmental Changes with Altimetry or ISAT teams. Interns examined altimetry projects and parameters over a wide range of global surfaces, including ice sheets, sea ice, vegetation, and ocean from 2 Earth-observing laser altimeters, the Ice Cloud and Land Elevation Satellite, ISAT, and the ISAT-2 missions. A special thanks to their project mentor, Christine Smirda, for her leadership and guidance. We will have 3 presentations from ISAT groups, followed by a Q&A. Please join me in welcoming the first ISAT team on examination of crevasse propagation in the Matanuska Glacier via ISAT-2.
Hi, my name is Chris Sorrell.
And my name is Lily Piasanen, and we are rising high school seniors from New York City and New Jersey, working under Dr. Christine Samerda on the ISAT-2 team focusing on glaciers. We want to start off with a quick explanation of exactly what glaciers are. They're defined as an accumulation of snow and ice with sediment and rock that move down a sloped area due to gravity. A great description for glaciers is that they're like incredibly old and slow-moving frozen rivers. Glaciers vary in region, but most are in Antarctica, Greenland, or other cold areas, and they also vary in size, but overall they have been shrinking and melting at higher rates than usual due to global warming.
We started our research process by examining the available literature on glaciers. We learned about the intricacies and the glacier anatomy, which is shown on the screen, and we read many papers on remote sensing of glaciers, as well as the factors that affect the rate of melting. One of those biggest factors are crevasses, and those are the cracks inside of glaciers caused by stress on different ice layers. They vary in shape and size, and they're also more likely to occur on fast-moving glaciers. And an example of one is featured on the right hand side of the slide. On the screen I have like a few different types listed. For example, bergschrunds form at the beginning of glaciers where they pull away from the rock wall at the head of it, whereas radial crevasses occur at the corner of a glacier.
Our area of focus for this research project was Alaska. As you can see in the graph on the slide, Alaska has a large section with glacial cover, particularly along the southern coast. We chose this region because of the limited other research done about these glaciers, and we wanted to fill in the gaps within the scientific community. In particular, we concentrated on the Matanuska Glacier, which is surrounded by 3 mountain ranges and melts into a river at its base. It's approximately 27 miles long and 4 miles wide, so it's a huge area of ice to analyze. At the moment, it melts and deposits into the river at about 1 foot per year, which, although it doesn't sound like a lot, is much faster than the rate the glacier can form. Our hypothesis states that due to climate change, glaciers have been melting at an accelerated rate, and one of the visual indicators of the process of melting is crevasses. Therefore, we hypothesized that over time there would be an increase in crevasses in both numbers and in size.
We developed a multi-instrument approach to fuse different products in order to evaluate crevasse structure as well as their appearance. First of all, we have ISAT-2, which is made up of 6 different laser beams that detect individual photons. It's 10,000 hertz, so it shoots 10,000 photons down to the ground and receives them back. We also use Landsat 8-9 imaging, and we pan sharpen them, as well as 2 other Landsat products, the fractional snow-covered area and the NDSI spectral index. We also use the Aster products, the visible and DEM. We use the ATL08 in order to map data on the photon scale, and that helped us to precisely measure latitude, longitude, as well as elevation. On the right, we have some featured software and websites that we utilize. First of all, QGIS was used to insert different layers. We have the Jupyter Notebook, which was used to run Python scripts, and Open Altimetry, USGS Earth Explorer, as well as NASA Earth Data Search were all forms of gathering data, and we use Google Earth Pro to map our final results. On the screen, we have a listed data table, and these are the 4 major instruments we use. We just want to give a big comparison. List our spatial resolution, temporal resolution, the spectral resolution, and the type as well. So Landsat is a visible and thermal sensor. The Aster 9 is a surface radiance radiometer. Aster 14 is a DEM, as I mentioned earlier, and ISAT 2 is a LiDAR altimeter.
Our key data tool was ISAT-2, which stands for the second Ice, Cloud, and Elevation Satellite, which was launched in the fall of 2018 and is still active to this day. It has 6 laser beams, 3 weak and 3 strong, that come in pairs, that pulse thousands of photons to Earth's surface and measures which ones return and how long it took for them to return. It has a 500-kilometer altitude and a 91-day repeat orbit. And most importantly, it houses the Atlas instrument, which we used for this research project.
On the screen, we have our different ATL03 and ATL08, which are ISAT-2 data products. ATL03 is global geolocated photon data. ATL08 is land, water, vegetation, elevation. And on the right, we mapped these files processed into KML files in Google Earth Pro, and these are the ground tracks of the ISAT-2 satellite. On the screen, we have our specific visual data products. We have Landsat 8-9, the operational land image. We have the Aster modeling product, that's the Aster 9. We have Google Earth Pro, as well as the NDSI, which is a spectral index for snow. Throughout our research process, there was a lot of data collection, but we also had to process all that data. So what we started with was finding the longitude and latitude of our location. That was listed early in the presentation. And we needed to process our visual files in order to reduce the graininess and increase the resolution. And we used the ISAT-2 products and we put them in for real in order to process our data. And those different results are listed on the right, and we use different files for different objectives. For example, the CSV files were used in the Python scripts and Jupyter notebooks, whereas the KML files were used in Google Earth Pro. We also had to go through and select the correct beam for optimal glacier overlap in order to choose which of the three listed were strong or best in our case.
These graphs on the slide demonstrate the change in elevation for certain time periods for the ground tracks from ISAT-2. As you can see, there are lots of peaks and valleys for each graph, which literally represent the physical crevasses and elevated portions. Although each band is taken from a slightly different portion of the glacier, these certain slices overlap, and in further research, we can analyze in depth the elevation changes of certain crevasses. Because the Matanuska is a northern facing glacier, as the x-axis gets larger and comes more north, the elevation decreases as the satellite approaches the terminus of the glacier.
This is just a continuation of Lily's previous slide. On the screen we have elevation averages mapped over time per season.
On this slide is our final graph, which compares crevasse propagation for select bands over time. To create this, we used the ASTER and Landsat 8-9 visible data to manually estimate the location and count of crevasses. The manual evaluation of the crevasses was compared with the visible data to those identifiable in the ISAT-2 tracks. As you can see on the graph, 3 out of the 4 subsets had an increase during the 5-year period. The most notable changes are in the winter 2020 band, which increased from 53 to 92 crevasses in the span of just 3 years, and the winter 2019 band, which increased from 30 to 43 over the course of 5 years. On the next slide, I will go more in depth on the visible data and crevasses for the winter 2019 band. This slide is just a highlight on the visual data for the winter 2019 band. As you can see on the slide, we have 5 years featured: 2005, 2016, 2017, 2019, and 2021. And this is just a visual representation of the data as well as a rough estimate of where the crevasses lie. Finally, we have the applications for our research. Overall, glacier research is vital to understand how entire regions and ecosystems react to our changing climate right now and predicting for the future. The examination of crevasses in particular serves to mark regional environmental changes such as temperature, wind, precipitation, and more, as well as the mark of glacier melting. The melting of glaciers have large environmental consequences, such as rising sea levels, change in habitats and biodiversity, as well as the loss of fresh water. And our research specifically provides analysis on a more remote and less studied glacier to the scientific community.
On this side we have the sources. Lastly, we'd like to acknowledge all the people that have helped us here today. I'd like to start by thanking our mentor, Dr. Christine Samerda. She's been super helpful over the past 4 weeks, whether that be through online lectures to working with her in person. We'd also like to thank Ms. Miller as well as Ms. Baggio for organizing this program, as well as the NASA STEM faculty, mentors, and chaperones for doing everything that supports us here today. Lastly, I'd also like to give a shout out to our ISAT-2 team for supporting us and all of our NASA STEM peers. As an aspiring scientist and researcher, NASA STEM has given me an opportunity to build upon my computational skills as well as collaborate alongside many talented peers.
Adding on to Chris, I found that working at SEAS as a NASA intern has given me the confidence, expertise, and inspiration to continue following my goal in pursuing engineering and environmental science.
Great job. So please join me in welcoming the ISAT-2 team and their presentation on monitoring wildfire-induced disruptions to vegetation health using remote sensing satellite data.
Hello, we are members of ISAT-2 under the guidance of Dr. Christine Samerda. My name is Carolyn He, and I'm a rising junior from New Jersey.
My name is Joanne Lynn, and I'm a rising junior from Washington. We are proud to present our research on monitoring wildfire-induced disruptions to vegetation health. Each year, wildfires across the United States inflict millions in damage to infrastructure, economies, and entire ecosystems. As wildfires become increasingly erratic in frequency and intensity, resources need to be allocated to monitor them. Thus, tracking vegetation changes over the duration of these fires is imperative to actively and effectively assess wildfire risk. This research endeavors to develop a comprehensive profile of vegetation disruption across a range of NASA satellites like ISAT-2, MODIS, and Landsat 8. We focus on 2 major wildfires in California, the 2018 Camp Fire and 2021 Dixie Fire.
We used the following questions to formulate our research hierarchy. First and foremost, we decided to look at vegetation health, and namely how it changed. So for that, we focused on the indicators of plant health before and after the fires, and we also looked at how vegetation indices such as NDVI and EVI can track both plant damage and recovery. Next, we looked at vegetation index and structure, namely, which plant species could be classified as the most and the least resilient, or how they may react differently to fires. And finally, we looked at the large-scale forest temporal data, namely, how physical changes to the impacted regions can be verified using remote sensing imagery. Through analyzing all these visual and spectral data points, we sought to verify the hypothesis as listed on the slide. The implications of our research are especially important in areas characterized by dry or volatile climates and with few existing resources to surveil wildfire conditions. The following table lists out preliminary background research on each of the fires we studied. What's important to note is that the Dixie and Camp fires occurred roughly in the same area, although not in the same time frame. However, they were similarly devastating in the scale and long-term damage they caused.
The first fire we will be reviewing is the 2018 Camp Fire. The exact coordinates can be seen on the slide along with images of the canopy height and ground elevation levels collected from the ISAT-2 open altimetry platform.
This is a forest profile of the area impacted by the Camp Fire. According to our ML tree species classification map, this region can be characterized as a largely homogeneous conifer forest, with the fir, pine, and aspen species being the primary ones sampled during classification and then studied during research.
The next fire is the 2021 Dixie Fire. Again, the exact coordinates and ISAT-2 canopy height images can be seen on the slide.
The Dixie Fire occurred primarily in the Plumas National Forest, and the majority of tree species impacted include, again, the fir, pine, and aspen families. Using the same predictive algorithm to map tree species classification onto the region, we were able to identify the primary species present in specific parts of the impacted region.
Next, we'll be going over the remote sensing instruments we used. Remote sensing is observing information of an area without physically making contact to the area. The table shown below describes the instruments we used, including the spatial, the spectral, and temporal resolutions. The Ice Cloud and Elevation Satellite, or ISAT-2, is a LiDAR altimeter used to evaluate the average tree height in the affected area. Next, the Moderate Resolution Imaging Spectroradiometer, or MODIS, is an instrument sampling the visible, near-infrared, and thermal infrared wavelength. Lastly, the Landsat A satellite is a visible and thermal sensor.
Throughout this research, we utilized data from the MODIS, Landsat 8, and ISAT-2 instruments. For MODIS, we looked at the products corresponding to vegetation health and surface temperature. Next, we also used data from Landsat 8, focusing on Level 2 data products, and created virtual rasters from specific band ratios for further vegetation analysis. And finally, from ISAT-2, we looked at ATLO3 and ATLO8 to measure the land and vegetation height. By using such a wide range of instruments, we aim to better compare indicators of plant health and therefore develop a more comprehensive profile for vegetation status pre- and post-wildfire.
For our methodology, we calculated 4 different vegetation indices: the Normalized Difference Vegetation Index, Enhanced Vegetation Index, Normalized Burn Ratio, and Vegetation Fractional Coverage. We then visualized band combinations that were used to review more vegetation indices.
The last point in our methodology trifecta was the use of supervised ML models, namely a CART, or Classification and Regression Tree predictive algorithm, to map burn severity and tree species over the regions of interest. CART utilizes a decision tree where each fork is a split in a predictor variable and each end node contains a prediction for the outcome variable. In our case, the predictive variable were the feature collections we manually imported into the model as training data, and to sample areas for training, we cross-referenced maps of native vegetation in California provided by calscape.org. Meanwhile, our severity map was validated using real burn severity maps released by Earth Explorer or the USGS, as well as special MODIS burn products, and overlaying classification maps for burn severity and tree species between both wildfires denoted the aspen and pine families as being the most resilient of the vegetation studied, while areas dominated by more vulnerable vegetation, like the Douglas fir, were marked as high risk for succeeding wildfires. Figure 1 exhibits how we referenced an actual burn severity map during the model training process, ultimately yielding an R-squared value of 0.84 for our classification map. Figure 2 is an image of our training and validation feature collections, with the colored polygons representing our geometric imports. And finally, our JavaScript code is captured in Figure 3. Note that we coded the entire model through Google Earth Engine, which is an online code editor with an access to a breadth of satellite instrument data. Now, let's get into the specific analysis and results for each fire.
First, to establish the scope of the wildfire, the burned area on the top left shows where the fire burned, and the thermal anomalies map at the bottom shows areas where the temperature is uncharacteristically hot or cold, but in this case, hot. The burn severity classification was derived from the previous two maps and shows the severity of the burns from the campfire.
In addition to burn severity and burn area, we also analyzed several vegetation indices, including NDVI, EVI, and FPAR, or the fraction of photosynthetically active radiation. From these cumulative analyses, a few distinct patterns emerged. Overall, graphed changes in vegetation indices corroborate different Landsat visualizations made in QGIS. Simply put, what we observed graphically matched what we also saw visually. The following graphs all show clearly how NTVI, EVI, and FPAR values decreased sharply following the start of the campfire, so November 8th. And pivoting to the EVI short-term time series to the left, we see how EVI decreases by 0.10 just a week after the fire began. And while this observation may be attributed to seasonal changes in plant health, the disruptions to yearly cyclical EVI patterns evidence otherwise. As the EVI long-term time series shows, EVI does not drop as drastically nor as severely as it did first following the fire. In fact, it took an assessed recovery time of nearly 5 to 6 months for EVI values to even return to a stable pattern, with EVI yet to return to its pre-fire level.
As can be seen through the data collected from the ISAT-2 satellite, the canopy heights of the vegetation before the camp wildfire had an average of around 50 meters, while afterwards the canopy heights were around an average of 25 meters. The Landsat 8 data shown below are the differences of the before and after data collected in the same area. The red part of the images show that the data had worsened conditions after the fire, while the green part of the images show improved conditions of the fire. The DNVR image indicates the burn areas of the fire, the DNDVI measures the vegetation health, the DVFC records vegetation cover, and the last image, DEVI, calculates vegetation greenness. Overall, the differences in the before and after image data are clearly identifiable in QGIS visualizations.
Next, we'll be going over our Dixie fire analysis. Using a similar process as with the campfire, first we analyzed and mapped thermal anomalies onto a region of interest by referencing specific MODIS burn products. The burn severity classification map on the right actually mirrors the official MODIS data products nearly perfectly. Analysis conducted on the Dixie fire had, by far, the most apparent impacts to vegetation, validated across indices and visualizations. As the NDVI visual time series shows, NDVI wanes in the triangular region during the course of the fire and continues to decrease until vegetation eventually regrows. Our graphical analysis for the Dixie fire most prominently displays an abnormal drop in NDVI, EVI, and additional vegetation indices post-fire, with the turning point hitting at approximately July 7th in all of the graphs displayed below. Regardless, the data tells a very steady story. Right at the start of the fire, vegetation indices decrease drastically, which is indicative of how fire adversely affects vegetation health. And these vegetation indices anomalies are still compounding over time, even marginally decreasing 2+ years after Dixie ended. And from this, we were able to assess that the Dixie fire had a recovery time of approximately 5 months, similar to the campfire, with long-term recovery still ongoing.
The ISAT-2 data shows that the average canopy height before and after the fire only decreased a little, but the amount of vegetation left decreased significantly. Like the Landsat data shown in the campfire comparisons, the red part of the images show that the data had worsened conditions after the fire, while the green part of the images show improved conditions of the fire. Overall, the changes in the vegetation are only slight and not drastically different. For future applications, we recommend 4 main points. First, to identify more areas that are prone to wildfires. Next, to collect long-term data and evaluate if plants adapt to wildfire conditions. Then, to broaden vegetation in samples by mapping more species affected by wildfires. And lastly, to replicate our methodology within another region.
We would like to extend our sincerest thanks to Dr. Christine Samerda, Margaret Baggio, and Selena Miller, as well as every incredible individual involved with NASA SEAS.
We know we will bring the knowledge and skills gained here into our future academic and professional pursuits. And here are our citations.
Thank you for listening.
Excellent research. So please join me in welcoming the ISAT-2 team and their presentation on integrating flood risk assessment maps and flood inundation maps, a synergistic approach for improved validation and prediction.
Hi, my name is Andy Wade, and I'm from Sugar Land, Texas.
Hi, my name is Onamika Chakraborty, and I'm from Northfield, New Jersey.
And today, we will be presenting our research on the integration and comparison of flood risk assessment maps and flood inundation maps to improve accuracy and prediction through machine learning and GIS. The goal of our research was to see if risk maps can be validated by comparing predicted risk locations with post-event inundation map classifications. We also wanted to use ISAT-2 data to validate DM products and identify erroneous potential areas caused by spatial resolution when used to create flood risk assessment maps. We also wanted to use a classification and regression tree predictive algorithm that is used in machine learning to create flood inundation maps from Sentinel-1 data. So what's the difference between flood risk assessment maps and flood inundation maps? Flood risk assessment maps evaluate and depict the likelihood of flooding in specific areas based on factors such as historical flood data, topography, rainfall patterns, and potential sources of flooding. Flood inundation maps show the extent and depth of flooding during an actual flood event, typically based on predictive modeling and real-time data.
Risk assessment maps are an indispensable tool that are crucial for first responders and disaster planners to reduce flood risk potentials and determine real-time event management procedures. The relevance of these maps continue growing as climate change exacerbates the intensity of extreme flooding events on both a temporal and spatial scale.
We use a multi-instrumental approach for our research, utilizing data from ASTER, ISAT-2, and Sentinel-1. First, we used ASTER on the Terra satellite to gather DEM data on the areas we were studying. We used ATLAS on ISAT to compare the ASTER data's accuracy, using the ATO3 and ATO8 data tools. Finally, we used Sentinel-1 data to visualize flooding in our areas of study through inundation maps.
We used Earth Data Search to get both ASTER and ISAT-2 data and the Data Access tool, and Open Altimetry to get ISAT-2, ATLO3, and ATLO8 data products.
We used 3 softwares to process and visualize our data: ArcGIS, FOREAL, and Google Earth Engine. ArcGIS was used to create flood risk assessment maps through DM data, FOREAL was used to process the ATO3 and ATLO8 data, and Google Earth Engine was used to create flood inundation maps through machine learning. We investigated 2 regions. First, we looked at Charleston in South Carolina, which experienced heavy flooding after Hurricane Matthew, which made landfall on October 8, 2016. Secondly, we looked at counties in southeast Brazil that are near the city of Sao Paulo, which experienced heavy flooding after torrential rain on February 19, 2023.
For our Google Earth Engine maps, we use Sentinel-1 synthetic aperture radar data, SAR, which is particularly useful in flood inundation mapping techniques due to the frequent revisit time, ability to collect images regardless of weather condition or cloud cover, day-night capability, and penetration through vegetation. As for our approach, we applied supervised classification using a classification and regression machine learning technique. We use Sentinel-1 SAR C-band data. There are 4 modes that Sentinel-1's radar can operate in. We are using the Infometric Wide Swath Routine Collection for Land, which is the main acquisition mode over land and is the one that is best used for flood mapping. The database used from Google Earth Engine is Sentinel-1 SAR GRD C-band synthetic aperture radar ground range detected log scaling. These images are all already analysis ready.
Creating a flood risk assessment map involves a systematic approach. First, DM data from ASTER was acquired through Earth Data Search. Next, the collected raster datasets were uploaded to ArcGIS, and within ArcGIS, the elevation data was visualized to map out the topographical landscape. The elevation was then categorized into 4 risk levels to assess flood susceptibility accurately. However, it's important to consider limitations. Elevation is not the only factor that plays into flood susceptibility, and an area of improvement would include having a weight overlay of more data features, including precipitation and vegetation. This is a flood risk assessment map of Charleston. We determined that Charleston has a relatively high moderate risk of flooding, and this is due to its low elevation. Along water bodies, Charleston has a very high risk of flooding, and as we moved inland, it becomes a moderate risk. In order to validate our flood risk assessment, we had to compare our DM data to ISAT-2 data, since ISAT-2 produces much more accurate data than ASTER due to its instrument. The ATO3 and ATLO8 data was processed in FOREAL, and the GroundTrack1 KMO file was plotted on the Charleston map. We then had to filter the GroundTrack data to remove the unclassified data points, and the map on the right shows the data points that we used to compare the DEM and ISAT-2 data. This is a scatter plot that compares the DEM and ISAT-2 data. ISAT-2 plots the ground, vegetation, and the top of the canopy, which is why there are 3 datasets for it. ASTER only includes DEM, so it has 1 dataset. The graph was plotted with northing by elevation, and the data for elevation are relatively similar, with only a few anomalies, meaning that our flood risk assessment map was rather accurate.
Why radar data from Sentinel-1? Well, Sentinel-1 synthetic aperture radar, SAR, is particularly useful in flood inundation mapping techniques due to the frequent revisit time, ability to collect images regardless of weather condition or cloud cover, day-night capability, and penetration through vegetation. There are 4 modes that Sentinel-1's radar can operate in. We're using the Infometric Wide Swath Routine Collection for Land for the purposes of flood mapping. The database used from Google Earth Engine is Sentinel-1 SAR GRD C-band data. As for our approach, we employed supervised classification using a classification and regression machine learning technique. This slide explains our basic, method, and process for the code. This video from the NASA RSET 2019 video series is what we based our models on and explains the coding process thoroughly. To dive into our process, firstly, we gathered the training data from the GEE database over our region of interest and on the days we are interested in. The before and after flood images may not be available immediately after or before a flood, so you have to adjust the time to when Sentinel-1 recorded data over that region. You must also apply a speckle filter due to the backscatter nature of the SAR data. Then you need to train your classifier to teach it what the visual change statistics look like, and you do that by creating layers of your different land covers you're interested in. So you overlay the training areas over the region and select areas that are representative of the backscatter that land cover layer shows. Here I am selecting flooded vegetation. Here is the before flood SAR image of Charleston, and then here is the after flood image. Here's them both so it's easier to visualize, and as you can see, certain areas appear brighter and there are visual changes due to the backscatter nature of those flooded areas and new darker areas from open water flooding. Here's a classification image that was created on Google Earth Engine through the CART machine learning algorithm and a key that shows the different land covers represented. CART is an incredibly powerful innovation in flood maps and semi-automatic classification of land cover changes that bring a lot of new insight to hydrological studies. However, this model does have some limitations which can be observed in this map of Brazil. This is the before image, and this is the after image. It is important to note that the time the image after the flood was taken is longer than the ones derived before Sentinel-1B was retired due to the revisit time changing. The classification map struggles with identifying the flooded vegetation change as there is a lot more elevation variety and a lot of vegetation, and there are many little changes in comparison to Charleston. It is also falsely recognizing the urban areas in the top left and on the right side as flooded vegetation because both flooded vegetation and urban areas exhibit the double bounce backscatter effect and appear bright, so it is easy for the classification to confuse them, especially when there is so much variation in elevation and there is heavy vegetation. Here is a close-up of those areas of flooded vegetation and of the urban areas, and as you can see, they both appear bright due to the double bounce radar backscatter nature. Overall, it is important to consider wavelength, polarization, and incidence angle when encountering limitations like these, as those parameters influence satellite response. Wavelength especially is an important parameter in heavily vegetative areas like the observed region in Brazil. SAR data is operated at the C-band wavelength, which has its own benefits, but there are longer wavelengths that can penetrate through vegetation canopy better. And here is a representation of how wavelength can influence detection of flooding. In the future, it would be interesting to look at this map from a different wavelength. So, to overcome limitations in these classifications in certain regions, different wavelengths can be considered. Urban areas can be better distinguished from flooded vegetation through selection of more representative data. Also, as stated by Erica Podest of JPL and NASA Goddard Space Flight Center, the use of texture measurements, which provide information about the pixels, can also help to distinguish those areas from each other.
This is a flood risk assessment map of some towns near Sao Paulo on the coastal side. We determined that there are some areas with higher elevations, which are mountain ranges, as well as lower elevation areas. We saw that the coastal side was very susceptible to flooding and had a high risk, and as we moved inland and past the mountain range, there was moderate to low risk. Similar to our process with Charleston, we have to compare our DEM data to ISAT-2 data, and these are the tracks and data points that we use to compare the data sets. This is the comparison graph of the DEM and ISAT-2 data for the towns near Sao Paulo. The scatter plot is graphed by northing by elevation, and we removed the initial northing data points since it indicated water. From the graph, we determined that the DEM was an accurate representation of elevation since the data points are relatively similar and that our risk assessment map for Brazil was accurate.
This research observes the synergy between risk assessment maps, elevation profiles, and inundation maps, working in tandem to help enhance flood prediction and validation processes. By leveraging risk maps, the accuracy and precision of SAR database maps can be effectively validated and refined. Furthermore, flood maps generated through CART can allow for the identification of previously unnoticed patterns, thereby leading to improved flood predictions. Flood risk assessment maps and flood inundation maps are important on their own, but together they powerfully complement each other to improve hazard management responses.
Thank you for listening to our presentation. We would like to thank the SEAS program for the incredible opportunity to work in a professional research setting with our amazing mentor, Dr. Samurda, who helped us extensively on this project with her dedication to our team and projects. We would also like to thank Mrs. Margaret Baggio and Mrs. Selena Miller for their hard work and effort for making the program as amazing as it is, and also the chaperones and faculty that helped put the program together. We were able to dive deeper into our passions and learn new skills
So we invite all three teams from ISAT to please turn on their cameras and their microphones. We have several questions for your group. We are going to start with team number 1. What was the rationale behind starting your data at 2018?
So to start off the question, so 2018 is when ISAT-2 began, and we wanted to keep all our data on the same time trail. There's some other instruments that had data available beforehand, but that aligned with our time scale, so we had to use the lowest common denominator.
And also for team number 1, how did you select the optimal beam that you chose for your research?
I could take this one. We wanted to look at only the strong beams. So ISAT-2 has 6 beams. We wanted to look at only the 3 strong beams. And then from there, we looked at which beam had the most overlap with the glacier. And that's how we selected. And it was different for every single year and season.
So how did you choose the Matanuska Glacier?
I can also take this one. I personally actually visited the Matanuska Glacier last year, but both Chris and I were interested in looking at a more remote glacier that has less scientific research done on it. And so we chose the Matanuska in order to fill in that gap in the field.
Great. Team number 2, what made you decide on the Dixie and Camp fires to focus on?
Yeah, so in our previous background research, before we actually started looking at satellite data, we really wanted to find wildfires that were closer together, so maybe we could compare the before and after effects of the wildfire. So we were lucky enough to find that in California, there was a Dixie and Camp Fire that were pretty close together in just different regions of like the same area in California. So that is the overall reason why we chose those 2 fires.
And also for team number 2, did you find out anything that surprised you as you were researching the data?
I can take this one. So as I mentioned in the presentation, we actually did observe an abnormal jump in the vegetation indices during the duration of the fire. And this was interesting because it was not only indicative of how the fire impacted surrounding vegetation, but it was also corroborated across different remote sensing instruments. So as we analyzed the MODIS, Landsat, and ISAT-2 data, we realized that we were seeing the impacts of the fire represented across a wide variety of the satellite instruments.
And also for team number 3, did you have any complications while creating the flood risk assessment maps?
Yes, we did have some complications, and I think our major issue is that we ran into issues with satellite data. Like some satellite data was really poor quality and we couldn't properly visualize it. And we used ATL3 and ATL8 first, but it was only a single line, so we weren't able to map out the elevation for certain areas. But then we ended up using Astro14, which gave us the DEM data, which we processed in ArcGIS to give us the elevation and flood risk maps.
And the next questions are for any of you to answer. Were your interest in climate data, what were your interests in climate data prior to attending SEATS?
I can take this one. So I think our group generally had like an interest in climate science and environmentalism before entering the group, and we try to incorporate it and integrate it with our passion for coding, as well as other computational skills. So I think we all had our specific interests beforehand, and that's why we split up into 3 groups, glaciers, vegetation, and flooding, and we were able to really delve into our interests, which we're really grateful to our mentor for allowing us to do so and supporting us along the way, considering that usually there are 2 groups for our team.
And will the knowledge that you received from your research done during the SEAS internship influence what you plan to study after graduating, or did it enhance what you are planning to study? So anyone on the ISAT team can answer.
Yeah, so I can take this one. So before coming to the SEES program, I was interested in computer science, and I didn't really have like branch out to any other fields like environmental changes and also using satellite data. So after experiencing this program, I think I'm really interested in learning more about like the space and just diving more into that. So I think that is what affected me during the program.
Yeah, and to bridge onto Joanne, what's really interesting about the SEES program is that you are given the opportunity to kind of delve into a very specific area of interest while also observing the intersectionality in generally space research. So this would encompass, studying environmental changes with satellite data or determining the age to an open cluster, as some of our other teams have been researching. And just from the discussions that I've had with some of our graduating seniors, I've really observed how all of us, as Chris mentioned earlier, are united by that interest in environmental science. And the fact that we're all students coming from various backgrounds who are able to merge that passion with either being computer science or policy or just environmental stewardship, it's been really heartening to see.
That's great. Well, congratulations to all of you on your research and good luck in your futures. So our next presentation is from the astronaut photography team. NASA monitors our dynamic Earth using a variety of assets, from Earth observing satellites to astronaut photography taken by crews on the International Space Station. During this project, interns worked with astronaut photography of Earth to gain experience with research, communication, and creating content aimed at producing a product that will enable the public to learn more about our planet Earth. Thank you to Rosina Miller from NASA's Astromaterials Department at Johnson Space Center for her guidance and enthusiasm. So please join me in welcoming the astronaut photography team with their presentation analyzing global changes over time through astronaut photography.
Hello everyone, we are the SEES Astronaut Photography Team. I'm Kai Hampelman, I'm from Golden, Colorado.
I'm Blaise Martinez, I'm from Lubbock, Texas.
I'm Bina Sarabi and I'm from Redmond, Washington.
I'm Robert Morris and I'm from Sewell, New Jersey.
I'm Dylan Hannon, I'm from Miami, Florida.
And I'm Jason Gruber and I'm from Stockbridge, Michigan.
Astronaut photography helps us study change over time because some changes that our world goes through are too slow for the naked eye to notice. Astronaut photography is just any image taken by an astronaut from space. This should be the space station, or prior missions like Skylab or the Space Shuttle program, etc. These images can be combined with satellite imagery and other datasets to help us get a full picture of how our planet changes both visibly and statistically, which allows us to find problems and propose solutions.
One of the first aspects we studied in our project was how urbanization can impact global deforestation and therefore affect other aspects of our global system. We started by looking at urbanization. As the global population continuously expands, the demand for resources, land, and food naturally increases. This increase in demand for areas to accommodate new people has led to the development of urbanization, where previously unused and sparsely populated land has been transformed into areas maintaining very large populations. Urbanization is a common global trend occurring over time, with nearly 60% of our current population living in cities and an expected number of 7 billion people living in urban areas by 2050. This correlates with higher access to education, electricity, better health standards such as nutrition and sanitation, clean water, and higher wages. While urbanization comes with many benefits to manage the inevitable growth of human population, its negative environmental impacts must also be considered. In order to develop cities, lands filled with biodiverse forests with unique ecosystems must be demolished to make way for an industrialized pollution center. So even though urbanization may improve the lives of people, it possibly creates a cycle of detrimental impacts to the same planet hosting the same population. With this, we hope to prove that increased anthropogenic urbanization over time will impact the rate of air pollution and biodiversity.
10 datasets that were used for the results come from the following sources. Tree sizes came from the ascent of the Amazon. Population density came from the Population Reference Bureau. Tree cut down dataset came from Latin American Post. Ocean carbon levels came from the Smithsonian Ocean. Biodiversity came from Greenpeace. Amazon species percentage came from Manga Bay. New Delhi urbanization came from NASA Earth Observatory. Urbanization effects came from USDA Forest Service. Urbanization charts came from Our World in Data. And the Mali forest cover came from earth.org.
Compiling data for research on the topic of urbanization, we used data from NASA's Earth Observatory where several images were sourced. Images of the city of New Delhi were viewed at different periods of time in order to observe a visual change in urbanization. Along with astronaut and satellite images, we analyzed graph data published by Our World in Data. The statistical data analyzed was sourced from the UN Population Division data, allowing for observation of accurate data trends of changing urbanization rates over time in various locations. The urbanization effects were also analyzed using verified sources and peer-reviewed research, such as research published by the University of Oxford and the USDA. One of the largest areas focused upon to analyze deforestation was the Amazon rainforest, as the Amazon is currently experiencing extreme levels of deforestation. Sources from the FAO have shown statistical data that was observed and used to come to our conclusions on the grand scale of deforestation in the Amazon. Additionally, forest coverage and images from other areas were analyzed, such as forest coverage loss in Mali, as well as data from the Population Reference Bureau, which was analyzed to clarify the relationship between deforestation and urbanization rates. Graphical trends were analyzed in depth in order to make the necessary connections for our final conclusions.
An interesting connection found throughout the study was a direct correlation between urbanization and deforestation. The rate of urbanization over the past years has rapidly increased and is projected to continue this trend through 2050, with an estimated increase of 4.2 billion in urban populations. Data found from a NASA database shows images taken from a satellite to capture the changes in the land of New Delhi in India. These images show rapid urbanization over the course of 31 years from 1989 to 2018. 3 images were captured of the city of Redondia by a satellite over the time period of 12 years. The pictures recorded here were from 2000, 2006, and 2012. Population density graph, figure 1, over time shows how the amount of forested land in the Amazon decreases as the area gets more dense with population. Information was found about the amount of carbon levels in the ocean from 1940 to 2010. During the year 1988, atmospheric CO2, seawater PCO2, and seawater pH levels became irregular at an extremely quick rate. When seawater pH becomes more acidic, the water can eat away at certain marine life such as coral and shellfish.
Our research concludes that there is evidence of a clear correlation between urbanization and deforestation. While urbanization usually causes deforestation, there is much more to the situation than just damage to the forestation of an area. For example, a major effect of deforestation is the disruption of the carbon cycle. When large portions of trees are cut down or removed, they release carbon dioxide into the air and give a similar effect to that of gas-powered vehicles. With the average height of a tree in the Brazilian Amazon being 100 feet tall, and over 1.6 million trees getting cut down annually, there is quite an alarming effect of deforestation. Another effect of the Amazon's carbon cycle being disrupted is an increase of ocean acidity. Most marine life is highly optimized to survive and thrive in their habitats. When a variable as dangerous as ocean acidity is affected, it could kill off most, if not all depending on severity, plankton, clams, shrimp, lobsters, coral reef, and other marine life. This damage is caused due to a lower pH level in the waters that eats away at minerals that these creatures produce. The final and arguably most important effect of deforestation is the negative impact it has on the biodiversity of the Amazon. The Amazon is home to 3 million unique plant, animal, and insect species that could easily suffer if rapid deforestation were to continue at this rate. This means the Amazon is home to 30% of total species in the world. These two topics were just a fraction of the bigger picture for global warming as a whole.
Some extensions we had with the research itself was when searching for datasets, there were often a plethora of options available at first. However, while narrowing it down to the ones relevant to our theme, specific places or times we wanted to look at, and other specifications, we ended up with only a few options available. So having an easily searchable database would be very helpful. On top of the research we did here, in the future we would like to look at how urban planning can minimize the impacts of deforestation. Although we may say this is inevitable, the point of this research is to shed light to the effects that are magnified through urbanization, so we can take the proper actions to reduce such effects in the future. If there was some sort of organizational structure where it was more effective in placing habitation areas or factories more efficiently so that not as much land was necessary, these could be ways to minimize the effects. Other research could be done to see if there was a better way to go about deforestation, such as not burning the forest so that the peat does not release CO2 as well. Other than that, it would be interesting to extend this research into real-life solutions through policy research. Now that we've learned about how deforestation can impact carbon cycles and biodiversity, just like many areas have carbon limits for corporations, we could look into corporations that profit off selling deforested land and how they are held accountable for the extra emissions they're impacting or the endangered species they're harming.
As mentioned, with urbanization and industrialization on the rise, as well as the global population, there is a higher demand for greenhouse gas emitting products. This increases the temperature of the air and oceans, which makes ice melt faster. Glaciers are formed by ice and snow building up over many years and not melting all the way during the summer. They move very, very slowly downhill under their own weight due to gravity. While most only move at about 1 foot per day, some can move faster or slower. They're definitely too slow to observe with the naked eye, which is where astronaut photography comes in. Glaciers act as an important source of fresh water, filling reservoirs, rivers, and lakes for millions of people to drink from. They also help shape the landscape, carving out rivers and valleys such as the Great Lakes. If all of the ice on Earth melted, the sea levels could rise up to 70 meters, and billions of people live within 70 meters of sea level and could lose their homes.
We use several sources and datasets to collect our information. Our primary dataset was the Images of Change Interactive on NASA's Global Climate Change website at climate.nasa.gov. This interaction gave us access to before and after astronaut photographs taken all over the world. These photographs, taken years or even decades apart, allowed us to see exactly what changed over time. Another dataset we found was the global surface currents provided by Carleton College. Their dataset shows the general temperature of the wind currents flowing through the oceans of Earth and provides an overview of global warming showcasing the human activity that causes the heat to increase globally. A graph provided by NSIDC gave us data proving an average decline in Arctic sea extent since 1980. When looking into population effects, we had to observe data showing a drastic increase. Our World in Data did a study on the global population in each country and included a linear graph representing the dramatic increase in population over the last 40 years. Population increase led to the higher demand in worldwide supplies such as food, home supplies, transportation, etc. The total carbon emissions per year has been steadily increasing as the population continues to exacerbate. Our World in Data also conducted a study on the annual carbon emission from fossil fuels and industrial revolution. Their data gave us a graph showing an increase beginning around the 1850s and rocketing from 1950 to 2021. Our primary data set was from our previous work in Module 1 when doing our SEAS training, knowing that the module provided links to climate and Earth-based data. Our second dataset module correlated with the idea of glacier melting, contributing to the evidence of climate change. The article from Carleton College also gave in-depth information on how air currents are studied and how they correlate with climate change, which leads to glacier melting.
The astronaut photography we used in our research included photos taken by scientists, astronauts, and satellites. Jesse Allen from 2001 to 2005 showcased the change in time of the Helheim Glacier and how it has melted in the 4 years it was observed. The operational land imager from the Landsat 8 satellite from January 2018 to 2020 was important because it showed the water that consequently melted on the George VI ice shelf due to climate change. The multispectral scanner on board Landsat 2 and the operational land imager on board Landsat 8 was used because it gave detail on the shrinking glaciers along western Antarctica from around February 1975 to March 2015. We also used mini graphs from our World in Data and NSIDC to see the correlation between many variables and sea ice melt as decades passed. As a group, we compared pictures taken at a certain time period focusing on specific spots near the North and South Pole to look for any drastic changes in water melt. We also wanted to figure out why these phenomena occurred. After we compared pictures and graphs of global sea ice taken during the time of the 50s to the 2010s and observed their transformations, we were able to see that the rate of glacier melting has increased significantly over the past few decades. The new inventions and way of society has caused an increase in greenhouse gas emissions, which has caused our Earth and sea to rise to dangerously high temperatures. This is what has caused the sea ice to melt. Limitations that we face were that only a few hundred out of around 200,000 glaciers are monitored. This lack of recurrent data points from the same location over time is a significant challenge because we were not able to go back to an exact point and compare. Another difficulty we faced was finding photos with even intervals over a long period of time. In the end, we had to focus on specific regions and glaciers, which in turn limited our conclusion. Overall, with the analysis, we were able to conclude that the glacier melting that occurred globally was an indication that there are multiple causes for the sea level rise. The datasets and photographs showed the rapid increase in sea level rise and glacier melt over time, giving us the details necessary to come up with our conclusion.
After comparing our datasets and imagery, we can see a direct correlation between population increase and ice melt. As the population increases, the demand for fossil fuels and other greenhouse gases also increases, which causes an accelerated warming. This causes the ice melting to accelerate along with it, which would explain why it can be seen that the population, emissions, and ice melt are all accelerating with each other.
Moving forward with our research, we can use photographs showing change in the past decades of sea ice to identify a problem and respond accordingly. We can also use this knowledge in further research to avoid many future issues and potentially save lives, and we want to observe what aspects of a major increasing population can have a direct correlation with sea ice melting, and we need to discover how we can turn around industrialization to have more eco-friendly solutions to reduce greenhouse gas emissions, such as switching to electric vehicles and finding more sustainable energy sources like windmills, etc.
Through this project, we were able to use photography taken by astronauts from a human perspective rather than satellites to analyze the slow changes of our climate features over time. Combined with numerical data, this visual evidence allows us to understand our environment to a deeper level, forwarding our sea level research and our urbanization research. I'd like to thank our mentor, Ms. Rosina Miller, and our assistant mentor, Ms. Floor, the NASA Seas and CSR administration who helped organize this program, as well as everyone else involved, and our parents for getting us where we are.
So we'd like to invite all team members from the astronaut photography team to turn on their cameras and their microphones. We have several questions for your team. The first question is, how is astronaut photography useful when we have data from satellites?
I can answer this one. All right, so it's not only useful because astronauts can think about their photos more. Like satellites are just taking photos of whatever they're orbiting, but astronauts can see something particularly interesting to them and document it themselves. So that way you're finding things that are especially interesting versus just random satellite pictures. And also astronaut photography data is a lot easier to sift through, A, because there's less of it, and B, I've just taken to more interesting things. And then also it's just good for the astronauts too. It's almost a hobby for them. So even in their downtime, astronauts want to be busy doing something. So astronaut photography is A, useful, and B, fun for the astronauts.
Great. Next question is, what regions would you recommend looking at to add and improve our current research?
I can take this
I can
one.
take this one.
Oh. You want to take it?
Yeah, sure, I got it. So as mentioned in our project, especially the Amazon rainforest was a key component, seeing that 30% of wildlife species are currently in the Amazon, as well as forested areas as Mali and other regions that are heavily forested are key to look at when covering deforestation.
Robert, did you have something you wanted to add?
Yes, I did. Basically, anywhere where there's not a lot of civilization currently, because we can monitor that over time, starting from now and onto the future. So places in the Arctic, like Dylan just said, anywhere in remote forests, deserts, anywhere where there's currently not a lot of civilization that we can easily monitor now.
And how did you narrow the large number of images and select the ones that you wanted to study?
I'll take this question. So when looking at the images of change on the climate.nasa.gov website, you're able to look exactly what you were specifically trying to observe. So we focus on glaciers, and when looking up glaciers, it shows you kind of the most recent to most biggest change, and ours happened to be the one in Greenland. So searching up specific terms on the website can give you exactly what you want to look for.
And did any of you have misconceptions or thoughts of what astronaut photography was prior to this internship?
I can start us off. Oh, sorry, Robert.
That's okay, you go.
Okay, so I can start us off. I did have a few misconceptions. I thought most places on the Earth were photographed basically every day, but that was not the case. There's lots of times where there's different spots on the Earth where they haven't been photographed in a long time. And I think that was one of the most challenging parts in our research, is that, we had to look at different spots because not all of them were taken every single day.
And another question, why do you think it's important to study things like urbanization when we know as humans development, it's going to happen anyway?
I can take this one. So through our research, we learned that although certain aspects like urbanization and deforestation may ultimately be inevitable, in order to properly mitigate these effects and processes in a manner that's beneficial to our global health and our human population in the future, we need to research and study the impacts of these processes. So like in our study and our research, our goal is just to understand how urbanization can create this sort of cycle of detrimental impacts to our environment, so that in further research that we'd like to conduct in the future, we can study how we can, as a civilization, make anthropogenic changes which could diminish this positive feedback loop that is forming. And although these tactics of urbanization and deforestation would likely still be existing, as that is kind of inevitable to society, we'd hopefully come up with solutions and technologies that can mitigate the effects that we've studied in our research.
So the last question is, when you looked at the photographs that astronauts took, how did you then select those images and the satellite data to connect those two different types of images?
I can also take this one.
You can take it.
Okay. Well, I think one of the misconceptions I had, and we learned over time, is that for astronaut photography in general, to kind of line up, since we're looking at change over time, to line up two images at the exact same angle, since they're taken in real time, it was really difficult to do. However, with satellite imagery, it's very continuous over time. So it was really easy to find certain aspects that were continuous with that imagery. And then based on the satellite data, we would have to find astronaut images that line up with the perfect angles that we're looking at that we would connect with. That's at least what our group did. So satellite imagery was really easy to find, but since astronaut data was so varied, it would be harder to line those up. But that's what our group did. Maybe the other group could speak to what they did.
Well, congratulations. You have something to add?
Yeah, I was part of like the glacier half of the presentation, and we did a really similar thing, except we would find the astronaut photography first, and then from there we could get like the coordinates and such of like the glacier that the astronauts were looking at, and then find similar satellite data, because there's always like astronauts heavily document what they take pictures of. They're like, all right, it was taken at this time, at these coordinates, like this point in our orbit, like so there's a lot of data, a lot of information about what is a picture of. So it's actually really easy to find satellite data that goes along with it.
Perfect. Well, you've done an excellent job with your research. Our next project is the Moon Exploration and Habitation Team. The interns worked as a team to investigate and design a lunar operations station. Their success in this endeavor required many areas of expertise, and each intern took on a variety of engineering or science roles that made up one cohesive design team. Through gaining knowledge of the most pressing and current scientific questions about the moon, the team chose the most appropriate landing site that will not only provide the best opportunity to conduct science, but also one that will provide valuable in situ resources that will be needed for sustained human habitation on the lunar surface. A special thanks to Dr. Ernest Lewis of the Astromaterials team at NASA Johnson Space Center for his commitment and dedication. So please join me in welcoming the Moon Exploration Team with their presentation on the All-Star Lunar Base.
Hello everyone, we are the Moon Exploration and Habituation Team, and for our project we were tasked with the creation of a lunar research base. The final product is called All-Star, which stands for Advanced Lunar Laboratory for Sustained Technological Analysis of Resources. Today, we will be going in depth to talk about the specific sections we were tasked in researching, but first I will introduce our team. My name is Hannah Burke, and I'm the Flight Logistics Specialist. Stella Chen is our Landing Site Specialist, Grant Kobos is our Architect, Aaron Kingsland is our Dust Mitigation Specialist, Annika Rao is our Research Technology Specialist, and Anushka Sharma is our AI Data Specialist. Our primary mission objectives include generally building our lunar research base to foster long-term habitation. We will be using in situ resource utilization and have a limited connection to Earth as a stepping stone for the potential of colonizing Mars. The first step to build a lunar research base is to actually get to the moon. I looked into two heavy launch vehicles that we could utilize for our purposes, NASA Space Launch System, or SLS, and the SpaceX Starship. The SLS was developed for Artemis, and I will focus on its Block 2 rendition because it should be fully developed by the time time we will be setting up our base. Block 2 has the payload capacity to carry 46 tons of cargo to the moon when it's in its cargo configuration, and it has 43 tons of payload capacity when it's in its crew configuration. It's estimated to cost $4.1 billion per launch, and it is a single-use rocket. In its crew configuration, it carries the Orion spacecraft, which can hold 4 to 6 people. Transitioning to the other picture, the SpaceX Starship can be seen in its crew configuration, though there's also a cargo configuration. The Starship is a combination of the Starship spacecraft and the Super Heavy launcher, created to conduct interplanetary transportation for up to 100 humans, scientific payloads, and other materials. The Starship is completely a reusable system and will have an expendable payload capacity of 250 tons and a reusable payload capacity of 150 tons. It is projected to cost $10 million per launch and will be used as one of the Artemis landers. The SpaceX Starship suits our purposes better and is the launcher we should use because of its higher payload capacity, reusability, and relatively cheap projected costs. The SLS would be a backup in case of any issues encountered with the Starship, which I will further discuss later. NASA's CLPS program, which stands for Commercial Lunar Payload Services, competitively funds companies to create lunar transportation services for NASA payloads. NASA sends requirements to companies and they are able to send in their bids for the spacecraft. NASA determines the landing site and payloads while the company is provided a grant to construct and control the spacecraft. We can utilize the CLPS program by putting out our requirements for our lander and fund a company to build it. The order of delivery is the least to most necessary aspects of the base. The first launch will be for the center module of the base, where experiments will be conducted. The second will be for the astronauts' personal living areas. The third will be for the rover and the garage, and the final launch will be for the plants and aquaponics area and systems. Science instruments and materials will be delivered throughout the mission. This is the work breakdown structure, which shows a more in-depth timeline. The work breakdown structure gets a little repetitive, so I'm just going to read the steps of the first launch. First, we need to acquire the Starship. Then, we need to acquire the first payload after we get the Starship, which will be the center module of the base. Then, we will load the payload into the Starship using the crew configuration, payload supports, and people to load it. Finally, we will conduct our first launch using the Starship system, a ground control crew and equipment, and a prepared launch site. There are two main risks we need to evaluate when it comes to the flight logistics aspect of the project. One, the Starship costs more than expected. The consequence is really unfortunate, and we would need to reevaluate and compare the SLS and Starship to see which has the better value. The likelihood is medium, because space travel is expensive, but it will be cheaper if the rocket becomes completely reusable. The second risk is the Starship is not fully developed or tested on time. The consequence, we have the SLS, but it would throw off the timeline of delivery, and the likelihood is low because they are using the Starship with Artemis, and Artemis will be finished before our mission. To summarize the flight logistics aspect of the project, we will be using the Starship and conducting 4 total launches to deliver the materials needed for the base. We will also competitively fund a company to build a lander using the CLPS program.
I'm Stella, and we considered many factors when choosing a landing site, but these are 3 of the most important. Water harvested from ice and PSRs can be used as drinking water for astronauts, so PSRs must be easily accessible from the landing site. Next, sunlight is an important energy source, and long periods of illumination are important, so astronauts working outside the moon base can see while they're collecting samples and doing other work. Lastly, landing in a safe area is a priority because sharp rocks and uneven terrain could potentially damage parts of the moon base or other instruments. We especially prioritize mitigating lunar dust. Lunar dust are small, sharp, and toxic regolith particles that can get into your eyes and throat, causing irritation and damage. It can become especially difficult when scratching solar panels and getting into the small crevices of instruments, making them unusable. This was a big concern when landing our lunar base. With these factors in mind, we considered 13 landing sites when determining where we wanted our research base to be located. However, based on the factors we prioritized, we chose these 3 sites as the final candidates. The connecting ridge was the most illuminated landing site, so it would help with solar panels and outside work. The Munson Rim would minimize damage to instruments when landing, and Leibniz Beta Plateau would maximize the amount of water harvested from lunar rocks. After discussing the landing sites, we settled on the connecting ridge. We came to the agreement that light and illumination from the sun was the most important factor to consider, and the ridge is the most illuminated location at the South Pole with a maximum of only 4 to 5 days without sunlight. There are also many PSRs within close vicinity, so we can extract water from the rocks and water ice. The connecting ridge is also located near the rim of the SPA basin, which is the largest, oldest, and deepest crater on the Moon, allowing us to learn more about the formation effects of the basin. Similarly, there is a lot of ancient rock material that can help us to better understand the formation and differentiation of the Moon. And here on the right is a picture of the SPA basin, and you can see how the South Pole is at the bottom near the rim of the basin. Here is a map of the lunar South Pole, and circled in blue is where the connecting ridge is located. It connects Shackleton, Day Gerlache, and Sverdrup craters. This is an illumination map that shows the average illumination on the connecting ridge. You can see here how there's a good amount of black area, meaning that illumination is extremely high in these areas. So for the trajectory of where we want to collect samples, it's important to collect water samples from multiple PSRs. This is possible because the connecting ridge is only 10 to 15 kilometers from both small and large PSRs. Then, exploring the ejected materials scattered on the surface of the connecting ridge could allow for reconstruction of the age and learning the effects of the formation of the SPA basin. Overall, making sure a variety of samples are collected so scientists can use these samples to determine more about the Moon. This map shows a faraway look at the general areas of where astronauts can travel to get to nearby PSRs. This is a close-up on the PSRs that are surrounding the ridge. All the red spots are PSRs. Here is a map of the SPA basin. Circled near the bottom is the South Pole, and you can see how it is in the mixed ejected material ring, so a lot of ejected material can be collected from this ring. Lastly, circled here is where the connecting ridge is located. The connecting ridge location is able to provide ancient rock samples from the feldspathic highlands terrain. Overall, we chose the connecting ridge because of its illumination, close proximity to multiple PSRs, access to ejecta in the SPA basin, and variety of samples, while considering factors such as landscape, dust, water, and illumination. The trajectory we chose reflected these unique features of the landing site, making sure to tackle previously unexplored areas and collecting different samples from each spot.
Hello, I'm Grant, and I'll be talking about the lunar habitat. The lunar habitat will be composed of 5 distinct modules. The laboratory and the airlock will be sent first, as they are necessary for the crew to survive in it. It will then be followed by the crew quarters, then the rover garage, and then finally the aquaponics bay. On the lunar surface, there is no atmosphere, which means that nothing will slow down projectiles such as debris, kicked-up rocks, or asteroids. Designing an unprotected lunar structure is irresponsible and dangerous. Each wall will be 100 millimeters thick. The first layer of the wall will be 3 sheets of 5160 steel and 2 sheets of depleted uranium. It will be 50 millimeters thick. The second layer is 30 millimeters thick and is made up of rubber and empty space. The third layer is 20 millimeters thick and made up of ceramic tiles and stainless steel. The 50 millimeter outer wall is a dense blend of hard and malleable metals. It will stop most projectiles and electromagnetic radiation. The 30 millimeter spacing forces kinetic energy to only be transferred through the rubber points, dampening any vibration and stopping cracks from occurring down the hole. The 20 millimeter inner wall will stop spall ejected from the outer wall. This armor configuration would be lighter, cheaper, and safer than just a solid wall. As it's lighter, it's easier for astronauts to assemble on the work site, as they don't have large construction equipment. It's also cheaper, as using fewer materials costs less. And it's safer because it stops spall fragments, which can be ejected even if the outer wall isn't penetrated. It prevents cracks from forming down the entirety of the structure, and it dampens vibrations. It also shields astronauts from electromagnetic radiation, which can potentially harm them long term. Overall, the structure is bulletproof, blast-proof, quake-proof, and crush-proof. It costs $13.2 million and weighs 547 tons, making it the largest structure to be in space.
Lunar regolith is a general term referring to debris covering the lunar surface. Considering the interactions researchers at the lunar base will have with these components, understanding and ultimately overcoming the harmful impacts that Stella described will be vital to the sustainability of our project. This effort begins with mitigating the researchers' exposure to lunar dust. To combat lunar dust, we can use the regolith's electrostatically negative properties to our advantage through repulsion. Dielectric wires, which can hold electrostatic charges with non-vanishing dipole moments, can be integrated into our project design to repel dust. Polysilicon elastomers are best suited for handling the lunar environment. We can integrate these dielectric wires into the designs of solar panels to prevent dust from settling on the solar cells and on communication systems that may prevent crucial signaling pathways. These will be utilized in Omika's rover designs with attractive forces to collect dust. However, repulsion is not foolproof. For the instances where lunar dust comes into contact with the EVA suits, how the fabrics are designed and organized can play a role in mitigating dust interactions. The Apollo 11 mission suffered from under-preparation, as the fabrics used for spacesuits were easily penetrable from the small grains. Artemis and future missions must have improved anti-abrasion properties through the use of multi-layering, seal protection materials. Based on NASA's studies on fabric penetration and dust abrasion, Kevlar and orthofabric should be the primary layers of the suit. Alongside this, surface nanocomposite coatings could further aid in dust repellency and surface protection. Despite these efforts, lunar dust will still lodge itself into the EVA suits, leaving filtration measures in the airlocks as their final resort. When the astronaut walks into the airlock, they will perform a series of rotations under high-speed projections of negative air ions. This will be accomplished through corona discharge with high curvature favorability of the cathode. The negative air ions will provide kinetic and repulsive forces to dislodge the particles from the spacesuit. The air and dust will travel into the circulating ventilation system, where the air will be neutralized through interactions with positive air ions created by another station of corona discharge, this time favoring the anode. The neutral air and dust will be separated through systems of electrostatic attraction and filtration. As a final measure, the astronaut will scrape more potential dust particles from crevices using a brush with electrostatically negative charge bristles. Different sized particles respond to electrostatic attraction based on their surface area to volume ratio. Therefore, when filtering the neutral air from the dust in a recirculation system, the smaller particles will respond favorably to electrostatic filtrations, while the larger particles can be reliably filtered with HEPA filters. Moderately sized particles can be filtered through electrostatics under low kinetic energy. Therefore, small corridors of 90-degree angles can achieve these slower speeds, and a high-grade HEPA filter can catch any remaining particles. A crucial goal of our lunar research base is to be self-sufficient with little to no need for resupply missions, meaning we will have to utilize the regolith despite its harmful properties, and this begins with how we collect the materials. The dust collection system will create an electrostatically positive field to attract small, loose dust particles surrounding the base. Once sensors have detected that the dust capacity has been met, the lid will close, self-seal, and create an airlock. Once the seal is complete, the vacuum will suck the sample into small, airtight containers for research or utilization purposes. Now that we have large samples of lunar dust at our disposal, let's take a look at how this can be used in a practical sense. Redwire regolith print is a technology that helps prove the capability of 3D printing on the moon using melted lunar dust. Due to the lunar gravity being about 1/6 of that of Earth, technological boundaries had to be surpassed. To do this, our RP utilizes a polyethylene filament to reliably bind layers and serve as a smooth outer layer. It also uses mechanized movements to discount gravity as a factor. With this technology, creating handheld tools and prototypes can aid researchers in their long-term goals by not having to wait for resupply missions to act on their visions. The production of hollow objects can wait until the lunar base is complete to make initial flights more spaciously productive. For mental health purposes, researchers who could potentially stay for years at a time could create personalized items. For the ultimate goal of self-sufficiency, in-situ resource utilization will play a large role in this effort. ISRU uses the materials readily available on the moon to generate necessary resources for a long-term presence. Through heating and liberating the regolith, oxygen molecules can be removed from the remainder of the sample. However, this heating process requires more energy than it would be worth for the oxygen we get out of it. Therefore, a better alternative would be the electrolysis of ice crystals found on the permanently shattered regions of the moon due to their time-efficient and resource-conscious nature.
One of, if not the most important objectives of All-STAR is to conduct in-situ research, which is why experimentative and innovative technologies are a necessity on the base. The specialized technology we will implement into All-STAR is a lunar sample collection rover, and we will also utilize a pressurized human transport rover and autonomous surgical technology modified for research purposes. Starting with the most important important design, the blueprint on the screen displays LROSCO, or the Lunar Rover for Sample Collection, whose purpose is to travel outside of the landing site and collect varied samples and camera footage to analyze back at All-Star. In terms of general specifications, Roscoe's estimated cost is $600 million. It has a weight of roughly 1,500 pounds, dimensions of 5 feet squared by 8 feet, a titanium alloy body, and active energy consumption of 600 watts. So let's take a closer look at the key details of this design. First off is the mast cam, which is a typical feature of autonomous rovers because it provides coverage and better understanding of surroundings. The mast cam is on a raised 360-degree rotating rod and includes an HD camera that can take live footage of the lunar surface to relay back to base and Earth, a small camera for high-resolution research snapshots, a floodlight for shadowed region travel, and a long-distance viewing camera to assist with hazard detection. Next is the top of the base, which is mainly for protection and power. The solar panels of the base provide main power when the rover is in direct light, and charge backup lithium-ion batteries for shadowed region travel, which can last upwards of 3 months. The panels are attached to the lid, which is automated to lift up and contain samples inside. The top also has multiple large floodlights to illuminate surroundings and improve camera function in the dark. On the right of the image, which is the front of the rover, the panel also automatically lifts to store attachments for the robotic arm. And this leads into the final section, which is the bottom of the base. This main portion includes a 3-jointed robotic arm with a customizable head, 6 large titanium and independently driving wheels, a hazard cam to detect the obstacles along the rover's path, and a radio wave sensor for similar function in the shadowed regions. Both the arm and the wheels are built with resilient titanium alloy to prevent damage from abrasive lunar regolith, which it will be in contact with nearly constantly. Additionally, the wheels are fairly large in size and number, have large twisting metal treads, and can move independently of each other, all to provide better maneuverability in unpredictable lunar environments. So how does Roscoe do its job of collecting samples? With the previously mentioned cameras and a variety of sensors which will be mentioned in the next slide, Roscoe can identify multiple different samples and which are most important to collect. The flexible robotic arm has detachable heads, meaning that the singular arm can be used for different functionalities, which is a very novel idea in rovers. The attachments are a scoop for small rocks, a strong 3-pronged hand for large rocks, an electromagnetic head as mentioned by Aaron for fine lunar dust, a rock drill bit with a protective cover for medium density rock, an abrasion drill bit to remove dust from mineral dense regolith, and finally a hard drill bit with a protective cover for regolith crust. Using the necessary attachment, Roscoe can extract samples that the system believes are important, as Anushka will delve into later, and store them in its body. The body of the rover consists of 4 raising platforms. On the left of the image, which is the back of the rover, the arm can place solid samples, with each level having a maximum payload of 40 pounds. On the right of the image, which is the front of the rover, the arm can stick its head into autonomous fine sample containers, which have opening and closing lids similar to a camera lens, to hold regolith samples while preventing internal damage to the rover as a result of stray lunar dust. The aforementioned sensors that assist the rover in finding the samples it needs are a Mars hand lens imager for astronauts to observe samples before collection, an alpha particle X-ray spectrometer for chemical compound identification in regolith, visual simultaneous localization and mapping, or VSLAM, to interpret sensor data in real time, an accelerometer to track Roscoe's health and speed, and various proximity, tactile, and position sensors to assist with navigation. While L. Roscoe is the unique rover for All-Star, current technologies can also be modified to have useful applications. Most notably, NASA is developing an astronaut transport rover for Mars that would provide shelter and a workspace for extended periods, which would be useful for astronauts to leave All-Star and do in-situ research in different lunar ranges. The other notable technology is inspired by Da Vinci surgical tools, which allow surgeons to connect to a pinpoint-accurate surgical system and conduct surgeries without ever touching the patient. With modifications and changes to the tools of the system, this technology would reduce damage to samples and astronauts during study and let them analyze anywhere at any time. So to summarize my main points, I discussed the importance of innovative research technologies, the most important to All-Star being L. Roscoe, which will allow the base to learn about the lunar environment. I also discussed the potential of previously existing designs to be modified to All-Star's purposes, namely the existing human transport rover and Da Vinci surgical technologies. And now we will transition over to my colleague Anushka, who will discuss what happens with the research done with these technologies.
I am Anushka, and to further facilitate the research, AI data flow models will be included. First, how safety systems will be integrated with the model. An early detection system will be established through the use of AI to allow for early recognition of malfunctions in the support systems. To establish this, we first will collect telemetry data, then develop relationships, and finally establish an alerts threshold. Telemetry data will be collected to develop sets of big data to later overlay with the real-time sensors of the base. It will be collected mostly through the ECLIS, or Environment Control and Life Support System of the moon base. Data such as air pressure, temperature, CO2 levels, which is under the Atmosphere Revitalization System, will be collected through this element. Radiation levels will also be collected and measured through dosimeters. This data will be constantly stored for the next steps of processing. After packets of big data have been recorded, relationships will be developed amongst each set. The usage of SIAT, or System Invariant Analysis technology, will be applied to determine and analyze relationships amongst the data over time. At the beginning stages of the moon base, past collections from the International Space Station will be utilized for big data sets to allow for the initial training of the model. Next, the SIAT systems will create invariant relationships to calibrate the models and understand the trends and possible irregularities within the sensors. The application of SIAT is most beneficial because it has the capacity to detect patterns in relationships that could otherwise be overlooked by professionals. In this image from the NEC Corporation, the first step of this process is depicted by representing how various sets of big data is accumulated and then overlaid to initially calibrate the system. Finally, after all the data has been collected and the relationships have been made, the thresholds for alerts must be established. Through the use of invariant model, the threshold for alerts is identified. When the values begin gravitating towards concerning values, the model is notified to send alerts. Predicted values are also calculated by the model. Thus, the predicted values are compared with the real-time data collection to understand if there is a potential threat that requires immediate troubleshooting. The diagnostic capabilities also allows for researchers to analyze and comprehend the process through which the model developed predicted values and alerts. This also greatly assists astronauts with troubleshooting, as it requires minimal levels of training since the technology provides detailed diagnostic features. In this image, as referred previously, it is demonstrated how an anomaly is detected in the system, as the real-time data is outside the established threshold, thus triggering attention towards the system. Next, AI models will also be integrated within the material identification systems. In order to pursue effective material identification, first the materials must be evaluated through various experimentations, then the data is analyzed, and finally the material is classified and identified. First, collecting the data. Experimentation is conducted on the materials to analyze their varying properties such as ionic conductivity, density, average volume, and molecular dynamics. The process of experimentation will occur with the assistance of the researchers. Next, the data will be analyzed through software models such as SVMs or support vector machines. Through the SVM, data training sets are established in order to assist the models in developing the ability to identify relationships. A diagnostic tree will then be used to and further develop the conjugate and relationships amongst the materials. Finally, after analysis, the materials will go through an identification process. For this, QSARs, or quantitative structure-activity relationships, will be used to finally understand the connections and categorization of the materials. This final step combines various properties of the materials to better identify them. Similar statistical models could also be applied. After collecting such eclectic pieces of big data, a storage element on the moon is necessary to allow for easy access to the data for the researchers. Thus, a data storage element will be included in reference to the space job IM-2 mission. This model is particularly well fit for our moon base because it is built to be in the South Pole with up to 16 TB of data. For this reason, a physical storage unit will be more convenient than an SSD card because not only does an SSD card require assistance from Earth, but it also has less storage capacity. Additionally, this unit has high-speed integration and allows researchers to have direct access to their data. Here is an image from the intuitive machines that is a reference to the space storage unit. In summary, SIAT technology will be implemented for early detection systems, QSARs will be used for material identification, and the IM-2 lander will be referenced for the storage unit on the base.
To reiterate, the objective of All-STAR was to create a safe long-term research base with minimal assistance from Earth in which astronauts could study and thrive on the lunar surface. We pursued these goals with the intention of preparing for future off-Earth research and habitation efforts, particularly on Mars, and we did so by mixing our own innovative designs with the modified creations of other scientific contributors to the new age of space exploration. As a team, researching and proposing All-STAR exposed us to a rigorous but rewarding STEM work environment, as well as peers with the same interest in space as us. The most challenging aspect of our project was converting our thorough research into a tangible idea that viewers could interpret, but we solved this through lots of planning and communication. We were able to learn so much from this experience thanks to our mentor Ernie, as well as our on-site supervisors and the constant support of the SEAS directors. Now we would like to individually tell you what we all gained from the SEAS program.
The NASA SEAS internship allowed me to recognize my passion for STEM-related careers such as aerospace engineering while collaborating with like-minded peers from across the nation.
Becoming a NASA SEAS intern is the greatest opportunity I have ever been given. It allowed me to make numerous friends from around the country and has given me more than enough memories to last a lifetime.
SEAS exposed me to authentic NASA research, and I was able to connect with and network with current and future subject matter experts through the program.
NASA SEAS has helped me realize all the different intersections between interests and has helped me meet a network of like-minded people. It has also sparked a new interest in me for aerospace, and I hope to dive further into it in the future.
SEAS introduced me to some great friends, colleagues, and field professionals and made me a better one of all of those.
The opportunity presented to me by NASA SEAS is a wonderful experience, and it's definitely the best thing I've done over any of my summers.
Here are the references used throughout the entirety of our presentation.
So we would like to invite the members of the All-STAR Lunar Base team to please turn on their cameras and unmute their mics. We have several questions for your team. The first question is, how will your rovers stand up to the extreme cold temperatures inside the permanently shadowed regions?
Yeah, so similarly to a lot of rovers that have been designed in the past, first of all, the walls are going to be absolutely insulated. So a lot of rovers use aerogel, but there are other materials that would be used to basically maintain the temperature inside of the rover. In addition, as I kind of explained in the design of the rover, on the back of the rover, which was the left of the model, most of the sensitive technologies would be stored there. And typically with things like that, there is usually a temperature protected box where you keep all of the most sensitive circuitry and things like that. So that would also exist inside the rover. And a lot of other rovers, which we would probably implement as well, typically try to use things like gold foil and different metals that can also reduce the amount of energy and heat that is transmitted outwards while the rover is functioning. So we would also implement that. And I just want to reiterate the fact that the Roscoe isn't meant to be going in permanently shadowed regions for a super extended period of time. If that were to happen, or if astronauts needed to be in the permanently shadowed region for an extended period of time to do research, they would probably take the human transport rover and go themselves, which would be far better insulated and be able to withstand the freezing cold temperatures for a longer period of time.
The next question is, how will you ensure that the uranium in your habitat walls does not produce harmful amounts of radiation?
So basically, it's not the harmful uranium, it's depleted uranium, which produces next to no harmful radiation. The rays that it produces can't go through your skin, so it's definitely not going through the sheets of steel that it's sandwiched in between.
So as a follow-on, what made you decide on the 3 layers of protection for the walls of the lunar structure?
The main concern is that if the wall were to get hit, even if nothing goes through the wall, it could send out harmful fragments from the other side of the wall that could damage components or harm people. So it's really just a safety precaution.
And what is the importance of the dust mitigation aspects of the base?
So these dust particles are highly abrasive and can really get into your lungs and damage your respiratory system. So on the astronaut EVA suits, these electrostatic repulsions can be used to repel the dust to, as it says, dust mitigation, to mitigate the amount of dust that will actually be able to adhere to the suit and potentially get into the lungs. And then for equipment malfunctions, for solar panels, if the dust can settle onto the solar panels, it will block the amount of potential energy that we could get from those high priority energy sources.
And the next question is, what was the best part of this particular internship for you?
The internship was definitely the people. And that includes both, the speakers, the mentors, as well as the other interns. As the team Moon Exploration, we got the opportunity to eat dinner with an astronaut one night, Dan Tanney, and that was definitely one of the coolest conversations that I've ever had in my life. So definitely the people was the best part of the internship.
Did you have the opportunity to review any of NASA's current plans for a moon colony?
Yeah, so we definitely reviewed a lot of NASA's current plans, such as looking into the Artemis mission and how it's taking first steps to try to establish a base on the moon, but also using the already chosen 13 candidate landing sites as a reference when choosing our landing site. And so we definitely did use pre-established research and expanded upon it.
Will the knowledge that you learned from the research on your moon habitat influence or enhance what you plan to study after graduating and going on to college?
Yeah, so I think researching this was really interesting. I researched the rover, and whenever you think about a mission like this, you always think about the larger part, so launching something, getting it onto the moon, and then just getting people to survive. But researching the rover and seeing all of my teammates' research really showed me all of the millions of little details that go into something like that. Like, you wouldn't think of dust mitigation as something that's absolutely necessary to a mission like this, and it really is. So even though I'm still very interested in engineering, researching the rover made me, after college, not want to look at the broader aspects, but maybe start to look into more of the specific things that a rover needs, like the batteries, and look into the smaller parts that are still absolutely fundamental, but that people don't really take into account as being necessary to the mission as a whole.
Kind of building.
Yes, go ahead, Anushka.
Building off of what Annika said, I think for me, I personally was delving more into the AI applications of this, and that is definitely a new area of research. So it helped me understand how it can be applied in broader missions, such as the Artemis missions and other areas of NASA research.
Great, excellent job, and thank you for your research. Our next project is from the Engineer Your World team. The team learned more about the mysteries of Venus with the goal of a slow, controlled descent to areas of interest, with a comprehensive plan to explore both the upper and lower atmosphere, as well as collect and identify ground samples to help tell the story of the once Earth-like planet. Interns were tasked to prototype, build with electronics and sensors, testing, and a final design based on the best researched and tested designs, as well as atmospheric and geographic research and site selection. A special thanks to their mentor, Stephanie Hanover, for her commitment and dedication. So please join me in welcoming the Engineer Your World team with their concept of our return to Venus.
Hello everyone, welcome to the Engineer Your World Return to Venus presentation for SEAS 2023. This year, our team has tackled the challenge of designing, building, and testing an entry, descent, and landing system for atmospheric and surface data collection on Venus. Our team consists of 10 people, but to increase productivity, we split into 2 teams of 5, Team Alpha and Team Sigma.
This is our mission patch. Its V shape represents Venus and our visionary mission, and the design itself displays Venus, Earth, and a distant exoplanet, similar to the exovenuses we hope to utilize our research to study. Now we will introduce members of our team from all across the country.
Hi, I'm Andrew Chichester, and I'm from New Jersey.
Hey, I'm Ethan, I'm from Pennsylvania.
Hi, I'm Fiona Mateo, and I'm from Florida.
Hi, I'm Jervis Benjamin, and I'm from Minnesota.
My name's Tiffany Palm, and I'm from Oklahoma.
Hi, my name is Aaron Lee, and I'm from Nevada.
Hi, I'm Enzo, and I'm from California.
Hi, my name's Harley Woltz, and I'm from Ohio.
Hi, I'm Siona Jane and I'm from Texas.
Hello, my name is Zoe and I'm from Missouri. Before we even started designing, we outlined a few mission objectives to guide us in our process. First and foremost, our main goal was to descend through the Venusian atmosphere as slow as possible to maximize data collection and learn more about its composition. Next, our goal was to explore the Venusian surface. Exploring both the atmosphere and the surface are particularly important because we have very limited data on either of these planetary aspects. Additionally, as with almost any planetary exploration mission, we wanted to check for any possible signs of life. And finally, the visionary goal of our entire mission was to apply our findings to understand the history of Venus and implications in the search for exoplanets.
To begin the brainstorming phase, each of our team members researched past missions to Venus and explored what worked, what didn't, and why. We each sketched 3 original designs, some of which are shown here. Our ideas included planes, gliders, capsules, and rovers, with aspects like parachutes, balloons, motors, and more. The range of ideas in the creative design phase was incredibly diverse because we had few restraints. After completing our designs, we reconvened and shared our ideas with our subteams. Each member analyzed the team's proposals and provided constructive criticism to better the blueprints of our peers' EDL system. Using our teammates' comments, we ultimately worked to create a personal final design. The next day, we each pitched our final ideas to our teammates. Combining the best aspects of each design, we finalized our sketch to scale for the prototype probe we will be working on for the next 2 weeks. In this process, we also focused on researching viable materials that could withstand the Venusian atmospheric conditions and implement them into our spacecraft.
The prototype for Team Alpha consists of a powered glider and a probe, which together could provide a more comprehensive analysis of Venus's atmospheric composition across various altitudes. Since the upper layer of atmosphere is slightly less extreme in comparison to the deeper layers of Venus, our team figured that a craft could stay there for a more prolonged period of time, while also having access to solar energy. As a result, we decided on a solar-powered glider with Teflon-covered solar panels that would ride the upper atmosphere, analyze dust particles in the high atmospheric layer, and use imaging technology to remotely peer into the deep atmosphere and surface. Since the solar-powered glider would be inefficient to fly in the lower atmosphere, the glider would then deploy a small probe which would fall into the deeper atmosphere so that a more in-depth study of Venus can be made. This small probe would initially use a Teflon-coated parachute to slow its descent, and after the chute became inefficient, the probe would cut the strings and rely on its drag fins to further slow down in a deeper layer. This design, where the 2 crafts are specialized for 2 different parts of Venus, allow us to study Venus as a whole while being able to operate for a more prolonged period of time. Now moving on to Sigma Team's prototype.
Our initial team design consists of 3 stages: a descent module, a lander, and a balloon. The descent module consists of a hexagonal pyramid capsule made out of titanium and protected on the bottom by a heat shield created with heat TPS material. Later, the heat shield is jettisoned and the trapezoidal sides of the capsule deployed to form air-braking fins which decelerate the vehicle to about 0.155 meters per second at a mass of 1,000 kilograms. As the craft falls, a Teflon-coated superpressure balloon inflates and detaches from the capsule, measuring elements of the atmosphere and adjusting altitude through a dual balloon system. Once near the surface, small rocket engines located near the fin tips fire and slow the vehicle down to a standstill midair, from which a lowering mechanism akin to the sky cranes of the Curiosity and Perseverance rovers places the spherical lander onto the ground, cuts the connecting cables, and flies away from the lander.
Originally, the descent stage design utilized a hypersonic inflatable aerodynamic decelerator, or HIAD, along with holding claws for the lander. However, in consideration of the thick atmosphere of Venus and the concerns with the lander falling out of the descent stage too soon, a normal ablative heat shield and a sky crane mechanism with a cable were used instead. The lander itself has a main pressurized body made out of titanium inner and outer skins, with an aerogel insulated fabric in between. Inside the pressurized body, a hemisphere with a low center of mass moves around using 2 wheels in contact with the outer sphere, allowing the entire lander to roll around in similar function to a sphero. Around the outside of the ball are several gates through which an instrument pole can extend from the inside of the craft to expose sensors to the outside Venusian environment, retracted after sufficient data collection to cool down in the controlled environment of the sphere.
Next, we started building. Creating a physical prototype from a conceptual design involved multiple intricacies. Yet through a challenging and sometimes tedious process, we ensured that the collaborative effort among our team prospered. Whether it be reshaping certain dimensions of our decelerating fins or expanding the width of a parachute, building our models allowed us to test our theories, see where we went wrong, and make adjustments.
As mentioned, Team Alpha constructed a prototype glider, probe, and parachute over the course of several days using a variety of materials such as foam board, foam sheets, string, and trash bags. Although our EDL model primarily consisted of makeshift materials like duct tape or foam board, the actual spacecraft for Venus will be composed of more sophisticated resources. To start, the fuselage of the plane will be built out of titanium. Titanium is an ideal material for spacecraft, not only because of its durability, but also for its resistance to corrosivity. The propellers of the glider will be made primarily from aluminum to maximize durability, and reinforcing them with nickel may also be helpful for excess safety precautions against atmospheric conditions. Shortly after ejecting from the dropship, the probe will deploy a large Teflon-coated parachute. Teflon will ensure that the parachute is protected against the sulfuric acid layer and Venus's hostile composition. Yet, upon all this search for materials, I came across two exceptional and recently discovered materials that are perfect for our capsule. Though expensive, tantalum and hafnium carbide can withstand temperatures up to 4,000 degrees Celsius, and they possess a durability unparalleled to previous resources. Outcoat tiles, also used on the Orion mission, will be incorporated into the heat shield as they are believed to withstand heat up to 5 times Venus's hottest recorded temperatures. As for sensors, the probe will have a dust mass spectrometer to determine what the Venetian dust is made out of, an ultraviolet and visible light spectrometer to determine the atmospheric composition by analyzing light, a thermal emission imaging system to distinguish variations in temperature, an accelerometer to allow for greater control while descending, and a Vendy camera to take infrared images of the surface. Here are a few videos displaying the testing of our spacecraft. Not only was it incredible to see our prototypes come to life, but also succeed in their goals of slow descent and atmospheric flight. Building our prototype was fairly straightforward, but definitely time-consuming. We had created blueprints, so we knew what the design was supposed to look like, but the most challenging part of this was figuring out how each material and design interconnected. You can see photos here of our build process. Some of the materials we used were corrugated plastic, cardboard, and fabric for the atmosphere module, and fluorofoam, wooden rods, and a styrofoam sphere for our lander. We also attempted to incorporate servos and motors to make the prototype more realistic.
Here are a few videos and images of our prototype test. We went through a total of 3 tests. The first was just for the fins alone to ensure they worked how we envisioned. Next, we attached our hardware and the lander's stand-in. This test ended up failing due to the lack of supports to prevent our fins from bending 180 degrees. We went back and reinforced the top with rigid dowels to prevent our fins from flipping back. This resulted in our final successful test.
Throughout our design process, we were fortunate to be able to meet with 3 NASA subject matter experts to discuss our mission with. First, we met with Dr. James Garvin, the principal investigator of the Da Vinci mission at Goddard Space Flight Center, who gave us insight on what materials and data we should use so that we would be able to effectively study Venus as a whole. Next, we met with Jeffrey Balcerski, a planetary scientist at Goddard. We discussed the landing site, Venetian atmospheric conditions, and replicating Venusian environments. Last, we met with Dr. Jeffrey Hall. He's an associate directorate technologist at NASA JPL. He and his team are currently testing a design of thin metal balloon coated with a Teflon, which in the Venusian atmosphere will allow for a much longer phase of data collection. Self-pressured balloons are one way to collect more data in the atmosphere by transferring gas between the balloon in the helium tank to pressurize for the specific layer of the atmosphere that it is placed in. Being able to stay in long periods of time in a specific atmospheric layers is fundamental to collecting lots and lots of data over extended periods of time.
After we compiled our research, we determined the landing site. Our landers will explore the northern areas of Venus due to their unique geological features. Our plane will fly at about 7 to 10 kilometers right between the atmosphere's supercritical fluid layer and cloudy layer. This will enable us to take the best quality images of each site we will visit, of which there are 3. Those being Cleopatra Crater, Lashimi Planum, and Fortuna Tessera. Fortuna Tessera is one point of interest because it is one of Venus's oldest geological features and presents incredible opportunities to investigate the history of Venus. Our glider will first make 3 imaging passes over the western parts of Fortuna Tessera before dropping one of 3 landing crafts over the site. Upon impact, our spacecraft will begin up-close imaging and analyzing of rocks in the area. Another designated drop site is Cleopatra Crater, an impact crater near the summit of Maxwell Mons. This crater is about 2.5 kilometers deep and 100 kilometers in diameter. The glider will complete 4 rotations above this site before ejecting its lander into the crater. Our lander will explore the layers of rock exposed by the impact. The last drop site, Lashimi Planum, is a plateau about 5,000 meters above the Venusian surface. Cursory images of this site from other orbiters have revealed that a sizable chunk of this site is composed of lava flows. Lava flows are of particular interest to our lander because investigation of the minerals within these lava flows can determine whether Venus was once Earth-like. The one major downside of this landing site is that its latitude makes it all very dark. However, using NiCad batteries, which we energized in the initial journey to Venus, we can power our plane and landers in darker times and places in the Venusian atmosphere.
Upon the approach to Venus, the powered glider will be released into the atmosphere with the 3 descent modules inside. In order to receive information from the landers, the data must be then transmitted to a spacecraft orbiting Venus, and from there it can be sent to the scientists on Earth. To do this, the landers will relay information to the power glider that will be in the upper atmosphere. The glider can then transmit that data to one of 2 crafts following an equatorial orbit around Venus. Between the orbiter from the Da Vinci mission and the orbiter that will be inserted as part of our mission, valuable atmospheric and surface data will be received every 40 minutes.
Now, for the results of the testing here on Earth. The first aspect of our testing was to examine the descent of our lander. At a 54-foot drop, the lander descended slowly at 1.3 meters per second for a total descent time of 13 seconds. This velocity translates to 0.016 meters per second in the Venusian atmosphere, and overall reached staggering success with fulfilling the goal of slow atmospheric descent for our spacecraft through the use of the parachute and its lightweight design. As for the powered glider, our team held various tests in an open field to test the stability and aerodynamic properties of our plane. We found that the control surface mechanism and ejectable hatch design were proven to be effective. We also made sure to focus on leveled and stabilized front wings, and that all wires and sensors inside the fuselage were connected for correct movement and a safe flight.
Overall, the glider achieved acceptable success through a meticulously engineered and aerodynamically optimized design. We observed the glider turning and taking off, and found that the glider is capable of sustained controlled flight, while also being able to carry and drop a payload, such as the drone, at the same time.
Thank you, Fiona. Now moving on to Team Sigma's design. The initial aerodynamic tests with a hexagonal capsule design were successful. We dropped the capsule from the 4th floor of the CSR building, and it performed very well. The video of the drop is shown here. The descent flaps opened immediately after the drop and allowed the capsule to slow down dramatically. In the end, it took 4 seconds to drop, and the effect of the descent wings on its deceleration are obvious.
For the final design, the glider from Team Alpha and the descent craft from Team Sigma were integrated into a single craft, with a scaled-up foldable glider housing 3 descent craft in a cargo bay, able to be deployed at particular points of interest. The heat shield of the descent craft is replaced by a simple fall-away cover protecting the base of the craft, and 2 drogue chutes deployed prior to decelerating fin deployment to prevent overstressing of the fins.
One of the many challenges we encountered during this project was designing around Venus's harsh conditions. Even though Venus is often referred to as Earth's twin because of the planet's similar sizes and masses, the atmospheric and surface composition, temperature, and pressure on Venus are contradictory to those of Earth.
Another challenge is that because Venus's violent conditions are challenging to manage, designing a lander that can survive these conditions and record data is very complicated with current widespread technology. Finally, designing a spacecraft for Venus's atmosphere but adapting it to test in Earth conditions was also difficult. Because we were unable to test our spacecraft in a simulated Venus environment, we had to make adjustments in order to accommodate Earth conditions like pressure, atmospheric composition, and temperature. Now on to our highlights.
Even though we faced many challenges, our mission delivered significant highlights as well. Our mentor was very kind in providing us access to almost any materials we needed. We participated in many hardware store runs and Amazon deliveries during our project building phase, and this almost unlimited access allowed us to design much more freely. Additionally, our team did a fantastic job collaborating with every member. We worked very well together, and each of us brought a unique skill set to the team. In addition to collaboration among all team members, we worked together in our subteams of 5, and even though each subteam was designing and building an entirely different system, we shared ideas and used other perspectives for our advantage. Finally, our ultimate prototypes were very functional. Even though we did not have access to hundreds of thousands of dollars worth of materials and technology, we were able to create some amazing prototypes with many functioning parts.
For future missions to Venus, new innovations in both material sciences and spacecraft developments will be imperative in creating larger, greater, and more in-depth missions. First off, gliders can cover and explore the entire upper atmosphere extremely quickly and effectively. A glider is also easier to steer compared to a balloon, which means we can control it to remain within a certain distance from our landers and maintain contact between the ground and the space probes to maintain communication. Next, landers that roll by displacing their weight would be great to create a never-before-seen traversable lander. Emerging materials and technologies suited for harsh conditions of Venus would allow more freedom to explore its surface. The ability for crafts, especially for a glider, to take advantage of both solar and extremely strong winds results in longer missions versus traditional fuel.
Now, looking at the applications of all our research. Understanding Venus is ultimately useful to fully define what it takes to be an exo-Earth. By redefining the lines of habitability, we can uncover if an exo-Earth is in fact more similar to an exo-Venus. Looking at the development of Venus to where it is today is the best window into looking for true exo-Earths. If we can successfully and fully understand how a Venus-like planet develops, we can limit the search of exo-Earths to what we know will contain long-term full habitability, resulting in a true exo-Earth. During a meeting with Dr. Jeffrey Hall from JPL, we discussed how many of the exoplanets we observe will be similar to Venus, since they'll be closer to their suns and easier to see. Because of the oncoming abundance of data on these exoplanets, it's important that we first understand a planet right here in our own solar system. Once we do that, we can apply those findings to exoplanets and learn even more about the origins of solar systems, galaxies, and the observable universe.
The feeling I got while working on our spacecraft, seeing everything come together, knowing that I could actually make an impact on real NASA missions, it was so cool and something I've never experienced before. That feeling has not only reaffirmed my career aspirations, but sparked new interest in other areas of study.
To me, NASA SEAS hasn't just been an internship. Throughout these past 2 weeks, I've learned so much about myself and engineering. As my team and I have struggled through the problems of landing on Venus, I've learned so much about the values of exploration, experimentation, and teamwork. And this internship has driven me to be the best version of myself. And for that, I'm eternally grateful.
I am immensely grateful for the opportunity to collaborate with such a brilliant team and to expand my knowledge on relevant, hands-on research for a prototype mission to Venus. The opportunity to contribute to real NASA missions has been an unparalleled experience that has inspired and enriched my passions for STEM beyond compare. I leave the SEAS internship not only with further confidence in pursuing STEM research, but also with invaluable skill sets that I will carry with me for the rest of my career.
I'd be more thankful that I was chosen for this opportunity to collaborate with a brilliant team and to design and prototype a mission to Venus. Not only am I leaving the NASA SEAS internship confident in my choice to pursue STEM and my abilities to conduct further research, but I have made invaluable connections with like-minded students and gained skills I will carry with me for the rest of my career.
I'm so grateful to have had an opportunity to do such challenging but rewarding work. I've always had an interest in aerospace engineering, but before SEAS, it felt like such a foreign concept. Now, the experience I've gained has made a career in the space industry seem much more attainable.
As my teammates have said, I'm incredibly grateful to be a part of the NASA SEAS internship. I've designed airplanes in the past, but this is the first time I had the opportunity to apply my experience on a mission to another planet. I love the challenges that came with this unique mission, and I hope to continue my involvement in space exploration into the future.
I have been so fortunate these past 2 weeks to interact with people from such different backgrounds and walks of life, learning more about others and myself in the process of pursuing a challenging, significant, and exciting goal like designing an EDL craft for Venus. And I can say no more than thank you for this opportunity.
I'm extremely thankful to have such a unique and amazing opportunity to present my skills. I've always been one to build things and work with mechanics, but this gave me a chance to test my knowledge. SEAS has improved my knowledge about space and taught me things about engineering I never knew.
SEAS has left me with invaluable experiences and has allowed me to try new things and learn new skills that I have never been exposed to before. I am so grateful for the opportunity to speak with NASA and JPL scientists and engineers and be involved with such a hands-on project. I'm also so fortunate to have had an amazing and supportive mentor that facilitated our needs and supported our dream.
SEAS was an amazing experience to develop and apply my love for science and chemistry in a group setting like never before. Researching Venusian gases and compounds and then applying those findings to physical sensors, especially when trying to detect biosignatures like phosphine, adds a whole new dimension to something that I love. Being a part of this program introduced me to all sorts of people from all parts of the country with all different backgrounds in life, taking me out of my comfort zone and resulting in a truly irreplaceable experience. Thank you.
First and foremost, we'd like to thank our incredible mentor, Mrs. Hanover, for getting materials for us, setting up meetings with Venus subject matter experts at NASA and JPL, helping us learn about the engineering process, and assisting us in any ways we needed. We truly couldn't have done this without her, and I know I speak for all of us when I say she's amazing. We'd also like to thank the SEAS program for allowing us this absolutely incredible opportunity. We've all had so much fun over the past 2 weeks, and we've gained so many valuable skills in space science, engineering, research, collaboration, and the learning process. Finally, we'd like to thank you all for taking the time to listen to our presentation. We've had a lot of fun going through this journey over the past 2 weeks, and we appreciate your dedication to hearing our ideas. And now let's open up the floor for any questions you may have.
So we invite the team to please turn on their cameras and unmute their mics. We have several questions for your team. The first question is, what part of the engineering design process required the most teamwork?
Yeah, so that's a great question. Looking back on our process, teamwork was most crucial when transitioning from our individual designs to a singular group design that we then built a prototype for. Because we had to start from such a wide variety of ideas and so many inputs from our diverse teams. And we had to narrow all those down to a single mission design through long discussions. It really, we really had to rely on the teamwork in that phase.
Yeah, so then going off of that, it's at this point that all of us really had to compromise and collaborate in order to produce the most effective design. This is because on each sub-team, taking 5 completely different ideas and combining them into one design definitely required us all to be open to new ideas and to work together.
And with what system is the glider to be powered?
So the glider will be powered by a nickel cadmium battery, which will take energy from the solar energy that comes from the Teflon covered solar wings on the craft. And in terms of thrust, it will be powered by a simple propeller system, which it will heavily rely on during the phase in which it carries the 3 probes. And after it deploys the 3 probes, it will adapt a more glider phase to conserve energy for its instruments and also to make maneuvers when necessary.
Given that titanium is expensive, hard to produce, and difficult to machine, do you think that the use of a different material might be more prudent?
Yeah, so that's a great question. While titanium is an expensive material, missions to such harsh and corrosive environments require resources that can withstand those said conditions. And so far, titanium has been the most cost-effective, durable, and reliable material that we have tested and used in the Venetian atmosphere. While we have found other materials, such as tantalum and hafnium carbide, as mentioned in the presentation, they prove more expensive, but their strength and durability is unparalleled to that of titanium.
Yeah, and even previously, we've seen titanium used in every single mission with the Soviet Venera and Vega missions. And in the future, with the new Da Vinci missions that are coming in the 2030s, they're also using a titanium spherical hull.
For the ultimate design in the Venusian atmosphere, what is the descent rate for optimal probes?
Thanks to the thick nature of the Venetian atmosphere, the drag flaps function incredibly well to slow down landing crafts, and the probes will likely land in around 7 minutes.
Okay, so thank you to the Engineer Your World team. Your research was amazing. We enjoyed seeing your tests. We will be taking a 20-minute break. We invite you to watch highlights of student accomplishments during the Earth and Space Science course. A special thanks to Teresa Howard and Asha Carmaker for scoring and preparing these highlights. We will continue with student presentations at 2:50 p.m. Central Time. Welcome back to the SEAS 2023 Science Symposium. Our next presentations are from the Meteorites team. A meteorite is a solid piece of debris from an object such as a comet, asteroid, or meteoroid that originates in outer space and survives its passage through the atmosphere to reach the surface of a planet or moon. During their investigation, interns learned how NASA researchers and how they search for meteorite samples and curate them, investigate the OSIRIS-REx and other asteroid missions. Thank you to Suzanne Foxworth with Jacob Technology at NASA Johnson Space Center for her guidance and dedication. We will have 4 team presentations followed by Q&A. Our first team researched carbonaceous meteorites and the origins of life.
Welcome everyone to our presentation. Today I, Rishita Agarwal, alongside my teammates Clara Allen and Sarah Krishan, will be exploring carbonaceous meteorites and their role in the origins of life. Our current understanding of the events that led to the origins of life on Earth remains limited, especially during the time frame between 4.5 and 4 billion years ago. So, in an attempt to shed light on how life might have emerged during this period, we extensively reviewed numerous online scientific studies and articles with a focus on carbonaceous meteorites and their composition. Approximately 4.1 to 3.9 billion years ago, the late heavy bombardment period occurred, characterized by a greater frequency of asteroid impacts throughout the solar system. An intriguing aspect of the late heavy bombardment period is the participation of carbonaceous chondrite meteorites of the CM2 type. Meteorites of this type have been found to contain a rich mixture of complex organic compounds, including proteins such as amino acids, as well as purine and pyrimidine nucleobases that contribute to the formation of RNA. This finding is significant because, according to researchers, the initiation of life requires the presence of RNA and proteins. Furthermore, the earliest signs of life discovered by scientists date back to around 3.7 billion years ago, which is relatively close in time to the late heavy bombardment period. This all hints towards that the late heavy bombardment period had something to do with the beginning of life. And so, this project specifically aims to investigate how carbonaceous chondrite meteorites could have contributed to the emergence of life during the late heavy bombardment period.
We determined our best approach would be to study the compounds found in carbonaceous chondrites, assuming ancient carbonaceous chondrites had a similar chemical makeup to the meteorites found in recent years, meaning organic compounds such as amino acids, alcohols, and sugars could have been delivered to early Earth. Specifically, amino acids and nucleobases have been found in CM2 meteorites such as the Murchison meteorite. The Murchison meteorite contains glycine, alanine, valine, proline, and glutamic acid, which are all protein-making amino acids. Scientists also found purines and pyrimidines on Murchison. Moreover, some CM2 meteorites contain the 5 RNA-DNA component nucleobases. They contain around 300 parts per billion of adenine, guanine, and around 50 parts per billion of uracil, but initially no trace of cytosine or thymine. However, after realizing the formic acid used to extract nucleobases was dissolving cytosine and thymine, scientists began to use cold water instead. This change revealed the presence of cytosine and thymine in CM2 meteorites such as the Murchison meteorite and the Tagish Lake meteorite.
Moving forward, research will be conducted into late heavy bombardment impact events on Mars, where meteorites, particularly carbonaceous chondrites, may have deposited organic compounds. Research should also be focused on the Moon, where previous Apollo mission samples have identified carbon compounds, particularly amino acids, in lunar soil. However, it is important to realize that these samples may have experienced contamination either through rock exhaust or solar wind, and not particularly through impact events. Nonetheless, identifying the presence of organic compounds in relation to meteorites on the Moon and Mars may suggest a relationship between the distribution of organic compounds on the aforementioned celestial bodies and Earth, which in turn would support speculation that it is standard for organic compounds to be distributed through carbonaceous chondrite impact events. Efforts should also be made into determining the process of complex organic compound formation in space versus on terrestrial planets. Through the Miller-Urey experiment, scientists Miller and Urey demonstrated how early Earth conditions could produce complex organic compounds such as amino acids, though the presence of organic compounds in carbonaceous chondrites is far more uncertain. Furthermore, because of the Miller-Urey experiment, it can be inferred that unless the rate of complex organic compound formation in carbonaceous chondrites is significantly higher than through the Miller-Urey process, then carbonaceous chondrites would not have had a meaningful impact on the distribution of complex organic compounds and subsequently life on Earth. Further research should also be done into the presence of RNA nucleobases in CM2 meteorites and whether RNA's other components, ribose and phosphate groups, also tend to be present in similar meteorites. The greater the number of instances of CM2 meteorites with all three components of RNA, the more plausible that meteorites played a role in the formation of RNA on Earth and influenced the evolution of life. Geologists finally should develop a stronger picture on the frequency and intensity of light-heavy bombardment impacts by studying spheral layers. Spheral layers are sedimentary beds containing spherules, or deposits of meteorite impacts formed from ejected impact melt or rock vapor plume condensates. They serve as markers for ancient impact events and can be used to study the frequency and intensity of impacts during certain time periods. A high frequency of impacts during the late heavy bombardment period would support the theory that the origin of life was influenced by impact events.
We investigated the potential relationship between carbonaceous chondrites and the origins of life. With this objective, our team learned of organic compounds found in CM2 meteorites. Amino acids and nucleobases were found to be the most relevant in our research. These monomers for proteins in DNA, RNA, both of which are essential to cell structure, lead scientists to believe that either compound was the first organic molecule on Earth. RNA carries the instructions for cells, and proteins are the material used to build cells and fulfill these functions. The existence of these organic compounds within meteorites indicates that organic molecules could have been produced abiotically and delivered to Earth during the late heavy bombardment period. These compounds could have provided Earth's source of amino acids and nucleobases that then evolved into early life. Based on this information, we believe carbonaceous chondrites, specifically CM2 meteorites, brought the components needed for early life to Earth.
SEAS has allowed me to connect with so many accomplished professionals who dedicated their whole life to the sciences. Their talks were so interesting and have inspired me to really continue pursuing my interest in astronomy.
This experience has allowed me to meet with NASA scientists in fields that I'm interested in and hear about the different paths they took in their careers. This will help me plan out my future education and career.
My experience with SEAS has educated me on how to conduct research projects and presentations. Through this program, I feel more prepared for my future endeavors. We would like to thank Margaret Baggio, Selena Miller, the University of Texas at Austin Center for Space Research, Suzanne Foxworth and Maritza Montoya, all the NASA ARES speakers, and all the SEAS speakers. Thank you so much.
Good job. Our next presentation from the Meteorites team is on determining the origin of meteorites through chemical analysis of isotopic composition.
Good afternoon, ladies and gentlemen. My name is Sofia Sassone, and the Meteorite Team 2, composed of myself, Annie Lee, Kira Aston, and Tanya BJ, presents to you our research into determining the origin of meteorites through chemical analysis of isotopic composition. Isotopic analysis of meteorite samples has been vital in determining their ages, origins, and location in the solar system. We determined that Martian samples' higher ratio oxygen 17 and 18 and excess xenon 129 helped identify their parent body. Lunar samples have almost identical oxygen isotope ratios to those on Earth, and differentiated meteorites and chondrites reveal distinct isotopic reservoirs, possibly isolated by proto-Jupiter. This approach also aids in dating iron meteorites with aluminum-26 and linking ordinary chondrites to S-type asteroids. Our goal was to determine how different isotopes can be used to determine the origin of meteorites, and what that analysis can tell us about the solar system. Isotopes are variations in elements that retain the same number of protons but have different quantities of neutrons, affecting these isotopes' weights and stability. They're measured using secondary ion mass spectrometry, where reflected ions from a sample are exposed to an electrical or magnetic field. Many of these isotopes, such as those of oxygen 17 and 18, undergo fractionation, where they get separated between different states of matter. The ratio of the separation in different physical processes on a body can be graphed. That, using data from the Earth, is known as the terrestrial fractionation line. Many planets have their own sort of signature of this isotopic ratio, which can then be used to identify whether a meteorite came from that planetary body. Protoplanetary disk, a dense envelope of gas and dust around a newly formed star, is where many early planets began to form, and thus began developing their own isotopic identifiers. From these bodies originate meteorites, some of which are known as chondrites, or stony meteorites that come from asteroids and contain small chondrules, which are spherical inclusions that contain material from the creation of the solar system.
Due to the wide range of our topic, we decided to focus on a select few isotopes and places of origin. We started by determining the places of origin that a majority of meteorites originated from: Mars, the Moon, and the protoplanetary disk. Then we determined isotopes that helped differentiate meteorites from those three places. These isotopes were aluminum-26, chromium-54, xenon-129, oxygen-17, and oxygen-18. All 5 of these isotopes provide valuable insight in differentiating unknown meteorite samples using isotopic ratios, general trends in the type of meteorite group, and knowledge of the composition of the parent body. We reference scientific papers that use methods like laser fluorination and secondary ion mass spectrometry to determine isotopic percentages in unknown meteorite samples. Then, by comparing the results to known origins of other meteorites or parent bodies, the origins of the unknown meteorites can be verified.
In our research, we found distinct variations in the concentrations of certain isotopes in meteorites from different parent bodies. Martian meteorites have been found to have a significantly higher concentration of oxygen-17 and oxygen-18 than other meteorites or terrestrial rocks. This graph shows the terrestrial fractionation line along with the Martian fractionation line, and the relative difference in concentration of oxygen isotopes in parts per thousand compared to a standard. So as you can see, Martian meteorites have a significantly higher concentration of oxygen-17, making them distinct. Martian meteorites have also been found to have a higher concentration of xenon-129 than other meteorites and rocks. The oxygen-17-oxygen-18 ratios have also been observed for lunar meteorites. The ratios found in lunar rocks have very little deviation from the terrestrial fractionation line. This matches the data found from lunar samples collected during the Apollo missions.
This graph displays the chromium-54 and oxygen-17 deviations from a standard terrestrial mass fractional line. By doing so, it shows a clear difference between differentiated meteorites and carbonaceous chondrites. We can see most of the carbonaceous chondrites, with a few differentiated meteorites in there, plotted along the right side of the graph, and a majority of the differentiated meteorites clustered at the left side. Furthermore, the isotopic ratios of the Moon, Mars, and Earth are located among the left side cluster. From this graph, we can conclude that carbonaceous chondrites are isotopically distinct from other chondrites, and the majority of differentiated meteorites are isotopically similar to non-carbonaceous chondrites. One factor that could explain this difference is the groups of meteorites forming at different places on the protoplanetary disk. As the disk grew, variations within the disk would have been reflected on the meteorites that formed there, leading to the trends observed in the graph.
As mentioned earlier, our research focused primarily on 5 isotopes: chromium-54, xenon-129, oxygen-17, oxygen-18, and aluminum-26. Firstly, directing our research focus to carbonaceous chondrites. Chromium-54 isotopes found in carbonaceous chondrites proved useful in determining the origin of certain meteorites. For example, scientists studying the Argyll and Murchison carbonaceous chondrites, which fell in France and Australia respectively, determined that the chromium-54 found within these meteorites originated from spinel, which are grains produced by supernovae that are known to be smaller than 100 nanometers. Given that refractory inclusions, like CAIs, tend to lack chromium, they cannot be the source of the chromium-54, thus suggesting that parts of these and other similar meteorites originated from supernova spinel. Calcium-aluminum-rich inclusions are rarely found in ordinary chondrites, but are found in much greater frequency in carbonaceous chondrites, which are accreted farther from the Sun, despite the fact that CAIs form near the protosun while exposed to radiation from solar particles.
Carbonaceous chondrites also have more refractory elements, such as calcium, aluminum, and titanium. The leading hypothesis for these trends is that elements within the refractory inclusions were transported from the region in the protosolar disk where they were formed by disk winds, and were then prevented from spiraling back into the inner solar system by Proto-Jupiter. Now turning to our research into Martian meteorites. Xenon-129 is found in excess in Martian atmosphere and soil, much more so than in Earth's atmosphere. Traces of Xenon-129 found in gas bubbles in Martian meteorites suggest Martian origin. Furthermore, oxygen-17 and oxygen-18 are found in consistent ratios in all studied Martian meteorites, creating a dataset to which isotopic composition of other meteorites can be compared against. Looking beyond gaseous or planetary parent bodies, chemical analysis of isotopic composition can also be applied to asteroid parent bodies. The Hayabusa 2 mission to asteroid Itokawa serves as an example. The ratio of oxygen-17 and oxygen-18 in Itokawa's pockets of olivine, orthoperoxine, and plagioclase indicates that the oxygen fractionated while in dynamic equilibrium between two physical states. This process is also known as thermal metamorphism. Given that this behavior was also observed in ordinary chondrites, it was determined that ordinary chondrites originated from S-type asteroids. Isotopic composition analysis can also be used in the context of dating. Aluminum-26 has a half-life of 717,000 years and can only form in hot environments, such as supernova explosions, suggesting that it was abundant in the protosolar disk. It is also produced due to spallation of silicon. Once entering the Earth's atmosphere, its production drastically decreases since the atmosphere erodes surface silicon. This allows aluminum-26 to be used for dating meteorites upon their entry into Earth. SEAS has impacted us all in unique ways. SEAS gave me the opportunity to explore a niche aspect of space science, equipped with the tools and skills to conduct research and collaborate with esteemed peers and professionals, further solidifying my interest in space exploration.
SEAS allowed me to dive deep into the mysteries of the universe and deepen my love for STEM, of which I will cherish in my future pursuits.
Thanks to SEAS, I have acquired invaluable insight into meteoritics and have gained a greater appreciation for research scientists. Collaborating with like-minded peers has been an incredible opportunity. This program has certainly reinforced my desire to pursue a career in STEM.
I am very grateful to SEAS for giving me the opportunity to work with incredible people from across the country and for letting me do research. It has let me explore my passion for STEM in a fun and engaging way, and I'll definitely treasure this experience.
Our SEAS experience was filled with many highlights, including having the opportunity to conduct research and learn new information, as well as to meet new people and learn from esteemed guest speakers and mentors. We also faced some challenges when it came to digesting scientific journals, compiling information, and understanding new concepts regarding the formation of meteorites and of our solar system. However, we believe that we have come out of the SEAS experience as stronger and more passionate STEM students.
We would like to thank Margaret Baggio, Selena Miller, University of Texas at Austin Space Center for Research, Suzanne Foxworth, and Maritza Montoya, all the NASA Ares speakers, and all the SEAS speakers. Thank you.
Good job. We would like our first two Meteorites teams to please turn on their cameras and unmute their mics. We have several questions for your teams. So the first question is for Team 1. What is a C2 meteorite?
So the C2 meteorites, it's a type of carbonaceous meteorite, and it has an abundant amount of hydrated minerals and then fine-grained matrix.
Also for team number 1, what did you enjoy the most from this internship?
I really enjoyed all the different speakers we had and like learning about all the different career paths they took.
Great. And what challenges did you encounter being a virtual internship?
I think Team 2 really hit on it about like understanding all of the scientific journals along with like just communicating with each other because we all live in different time zones.
And team 2, what was there anything surprising or interesting that you learned about meteorites after you were doing your research?
I can take this one. So actually, I learned so much about meteorites just from doing this internship and research in general. I mean, first of all, I didn't know there are so many different types of meteorites like chondrites, achondrites, carbonaceous chondrites, and etc. I've also learned that meteorites are great indicators of what goes on in our solar system. Like they can be used to analyze certain events that happened millions of years ago, or maybe places within our solar system that normally may be difficult to reach just by using their isotopic composition.
And also for team 2, what is CAI?
Sure, so I can take this one. So CAIs are a type of refractory inclusion. They stand for calcium aluminum rich inclusions. And they were actually one of the first solids that formed in our solar system just because they formed near the protosun under a lot of solar radiation. And we found CAIs to be really important for our research specifically in determining origin of meteorites, because if you find CAIs in certain meteorites and the refractory elements within them, they give you a lot of information about where these elements originated from. Especially in a protosolar disk, they give information about how disk winds transported them from multiple locations in the protosolar disk into the meteorites we see today.
So were you able to see virtually some of the meteorites that Johnson Space Center has collected? Were you able to see
this one? Oh, sorry.
Go ahead.
We were able to see a bunch of images and data sets from various meteorites collected by Johnson Space Center, especially those from the Altimetry missions. So those were collected in the Arctic, Antarctic, and yeah, it was incredible to see all the different formations that you could find within all these different kinds of meteorites.
Great. Well, thank you all for your research. And we're going to move on to our next team. So please welcome the meteorite team, unraveling the origins and evolution of terrestrial bodies through matching and volatile signatures.
Hello, everybody. This is Team 3 from Meteorites, and today we will be talking about unraveling the origins and evolution of terrestrial bodies through matching and volatile signatures. We have Inga, Ethan, Nafisa, and Angelina here today to present. So first up is our abstract. Since it is a little long, I will just be touching on the highlights of it. Some meteorites, like the Murchison and Murray meteorites, contain volatile substances like oxygen, water, noble gases, or acids that can reveal their origins. Learning about meteorite origins then reveals more about planet formation in our early solar system. We did most of our research through Lunar and Planetary Institute meeting abstracts, and the rest of it was through Google Scholar. Many of these abstracts went over methods to detect volatiles like petrographic analysis and gas chromatography. Introduction. Many of these meteorites or chondrites contain materials from the early solar system. These volatile compounds can be oxygen, carbon, noble gases, and types of acids like those found in the Murchison and Murray meteorites. Additionally, radionuclides can help determine the terrestrial age of the meteorite or its cosmic ray exposure, or in other words, its time spent on Earth and its time spent in space. Knowing about these volatiles tells us a lot about the origin and evolution of these meteorites and also matching them to other terrestrial bodies. As an example, volatiles like feldspar can form during heating events, painting a picture of the meteorite's past. Researchers often use petrographic analysis, thermoluminescence, or gas chromatography to discover volatiles. Finding out about meteorites' origins also tells us more about how the planets formed in our early solar system.
The methodologies used for this project was twofold. For volatile signature extraction, chemical composition of carbonaceous chondrite groups were extracted using radiochemical neutron activation and atomic absorption techniques to determine the level of volatile mobile traces in the meteorites they studied for the meteorites located in Antarctica. To determine the level of volatile mobile traces, solid phase microextraction was integrated with gas chromatography and mass spectrometry to distinguish over 50 monocarboxylic acids in the Murchison meteorite, which highlighted that acids have various structures, including straight chain and the branched forms. For the matching analysis phase, in order to find meteorite matches, researchers used trace luminescence, which showed that Antarctica meteorites tend to form within elongated fields, and showed that information in order to analyze cosmogenic mobile gas abundance and radionuclide activity.
Now, moving on to the results, we decided to focus deeply on the Murchison meteorite, which is a famous carbonaceous meteorite that fell near Murchison, Australia. Through research, I learned that it was paired with the Murray meteorite, which was found in Kentucky. To determine the matching between the two meteorites, I did research on their noble gas compositions and decided to focus on their xenon isotope ratios. After comparing the ratios through a dataset measured at the University of Chicago, I can infer that the meteorites originate from the same parent body. Next, to compare the volatile signatures, I found a dataset measured by the University of Bonn, which compared the abundances of sulfur, selenium, and tellurium in both the meteorites. This was measured through a process called isotope dilution, which is a method that accurately determines the concentration of a compound. In the bigger picture, both the Murchison and Murray meteorites are carbonaceous chondrites, which are rich in organic compounds and the building blocks of life. I believe that the delivery of the organic compounds to Earth contributed to the elements that allow life to form on Earth. On the left, you can see the table with both the Murchison and Murray meteorites. The abundances of sulfur are very similar, with Murchison at 29,170 and Murray at 26,060 micrograms. With selenium, Murchison had an abundance of 12.5 milligrams and Murray had an abundance of 12.47 micrograms, which is a very similar comparison again. Finally, with tellurium, Murchison had an abundance of 1.372, while Murray had an abundance of 1.44 micrograms. On the right, I used a dataset from the University of Chicago, and I graphed the ratios of the xenon isotopes of xenon-124, xenon-126, and xenon-128. And for both meteorites, Murray and Murchison, you can see how similar the bar graphs look in comparison with each other for all three isotopes.
Similarities between isotopes, reduced nature, and meteorite composition can tell us about whether two meteorites may have formed in the same region within the solar nebula. Analyzing the composition of meteorites using mass spectrometry has revealed correlations. For example, when comparing the compositions of the Altimetry meteorite and the Ulysses iron meteorite has displayed similarities in the abundance of schreibersite, a mineral rich in nickel. This suggests a common origin or related processes for these meteorites. Mineralogy and organic compounds in Murchison meteorites. Formic acid was one of more than 50 monocarboxylic acids found in Murchison, including straight chain and branched varieties. While branched acids reveals larger quantities of heavy isotopes, the isotopic ratio of monocarboxylic acids indicated a decrease with increasing chain lengths in straight chains. The evidence points to the formation of the monocarboxylic acids by space-based processes involving radicals and ions. Indicators such as radionuclide analysis and the noble gases found in meteorites sheds light on Earth's formation, the development of its atmosphere, cosmic ray exposure, and the beginning of volatiles on terrestrial planets. The isotopic fractionation in Martian atmosphere, nitrogen, hydrogen, and noble gases suggest partial loss of the atmosphere over time. When talking about radionuclide analysis, specifically the ratio of chlorine-36 to beryllium-10 in matched meteorites, which are found to be similar, indicating corresponding terrestrial ages of about 185,000 years. These ratios can also indicate the duration of cosmic ray exposure experienced by meteorites. Cosmogenic noble gas abundance and radionuclide activity are additional indicators of meteorite matching. Cosmogenic noble gases such as helium, neon, and argon are produced by cosmic ray interactions with elements in meteorites. Comparing the abundance of these gases can provide insights into potential matching of meteorites. When comparing the mineralogy and composition of meteorites through petrographic examinations, meteorites within the same petrologic class can exhibit similar characteristics. Carbonaceous chondrites are pristine rock samples of our solar system, known for their similar abundances of high-temperature components. Researchers distinguish matching of meteorites based on different heating periods and thermal histories by examining the thermoluminescence characteristics of the meteorites. Thermoluminescence analysis can detect feldspar in meteorites, aiding in meteorite matching. Thermoluminescence measures the light emitted when feldspar minerals are heated. Higher thermoluminescence values suggest heating events, indicating potential matching within meteorite groups.
To start with, I learned a lot about efficiently coordinating teamwork, how to conduct research through abstracts, and scientific writing. Additionally, hearing speakers talk about their jobs and answer our questions was very enlightening.
For me, being given the opportunity to listen to speakers such as astronaut Fred Hayes and their experiences working under NASA was inspiring to hear. I also gained a lot of insight and familiarized myself with an abundance of knowledge through conducting research.
This program left an incredible mark on me, fueling my passion for space and research. And being able to learn about the NASA scientists' experiences, collaborate and exchange ideas with peers, and conduct a research project in the end has allowed me to take my learning to a new level.
Overall, during my time here at NASA SEAS, I had a great time learning from the direct experiences from speakers here at NASA and going through all steps of the collaborative research process, from beginning with a topic to conducting thorough research.
So now moving on to our acknowledgements, we would like to thank Margaret Baggio, Selena Miller, University of Texas at Austin Center for Space Research, our mentors Suzanne Foxworth and Maritza Montoya, all the NASA Aries speakers, and all the SEAS speakers.
Good job. So our next presentation is from the Meteorite team, and they will present, could asteroids have brought life to Earth?
Good afternoon. Today we're going to be discussing, could asteroids have brought life to Earth? My name is Anisha and my team members are Eric, Roan, and Jeevan. This is our abstract, and I'll just be going over a few key highlights. Our group is going to be exploring the hypothesis of whether meteorite impacts played a role in bringing life to our planet. First, we're going to be looking at organic material on meteorites in order to see if this material could have transferred over to life on Earth. We're also going to look at the early history of Earth, where meteorites have been bombarding Earth since its formation, and seeing whether or not this is a time frame where life could have been brought over to Earth. Next, we're going to look at panspermia, which is the theory of life created outside of Earth, in order to see whether it was viable or not as to whether life could have been created outside of our Earth or outside of our solar system. Our team's research was mostly conducted through studying several research papers and scholarly articles. Overall, we concluded that meteorites do have an impact on bringing life over to Earth. Introduction. Our research will be divided into several different parts, where we will go into organic compounds in meteorites, panspermia, and the early history of Earth, and then we will reach a conclusion.
Before we talk about how anything came to Earth, I will talk about what was already here. At the beginning of the solar system, our sun was surrounded by a disk of gases and dust, known as the protoplanetary disk. It contained almost all of the materials found in our solar system's planets and asteroids. At first, it was relatively uniform in composition. However, our young sun was a lot more active than today. It emitted radiation in the X-ray range and created frequent solar storms. With so much energy emitted, the sun pushed the contents of the disk into different areas of orbit. Heavy elements such as iron and silicon remained closer to the sun, while lighter elements such as hydrogen were pushed away. Because of that, The 4 closest planets to the Sun have large rocky bases, while planets further away tend to be gaseous. Additionally, the Earth's layer started with lots of carbon, metals, and silicon. However, its orbit on the disk lacked the hydrogen needed to have water. For any kind of life to make it to Earth, it would need to voyage through some difficult conditions. Around the time when life would be traveling to Earth, solar rays were a lot more powerful than they are today. The sun emitted electromagnetic radiation all the way up to the frequency of X-rays. But there's an organism that can survive in extreme conditions. In fact, while we often assume that bacteria would be the only resilient organisms to make it to Earth, there's a certain animal that can survive extreme conditions. It's called a tardigrade, and it is commonly known as the water bear or moss piglet. These organisms are so resilient they can survive in numerous hot, cold, and desperate conditions. When researchers placed tardigrades under 2,000 gray of X-ray radiation, they observed almost no disturbances in the ecosystem. The water bears continued to move around like normal and laid eggs as though no environmental stress had been put on them. Although they were likely not the organism to arrive to Earth, they proved that there are genetic mutations that limit the effects of the bombardment of solar radiation on an organism's cells.
Some bacteria have been found to thrive on iron and rust, making it even more possible that a colony of bacteria could survive for over a decade on an asteroid. The following is a graph showing how a significant amount of Deinococcus radiodurans were able to survive 3 years in space.
Setting the stage. The Earth went through a lot of activity in its early stages. It was molten all the way to the end of the Hadean Eon. At the start of the Aegean Eon, the Earth started to have a crust. In fact, it became so cold that 3.8 billion years ago, an ocean's worth of water rained at once. The Eon is important to our search for the origins of life because our oldest fossils date back to it. Thus, as far as we know, it was the beginning of life. The fossil dates back to 3.5 billion years ago, which is around the time when the magnetosphere fully developed. One possibility for the earliest life on the surface is that it could have waited underground. In this possibility, any bacteria that left the ground before the magnetosphere would die before they could spread. This theory would explain why our oldest fossil dates back to the same time as the establishment of the magnetosphere. Let's talk about some underground bacteria. At the top right, there is Johannesburg. And under Johannesburg, specifically 2.8 kilometers under Johannesburg, a colony of bacteria was found that had sat locked away from the surface of the Earth for millions of years. It was the only species found in the entire ecosystem, meaning it was completely self-sufficient. Being lonely and deprived of both water and sunlight, the bacteria relied on surrounding compounds for sustenance. For energy, the bacteria break down sulfate. For nitrogen, essential for the production of protein, the bacteria break down ammonium. And for carbon, the bacteria rely on formate.
Composition. So scientists have detected bits of adenine, guanine, and other organic compounds in meteorites since the 1960s. And after this date, they've also found cytosine, uracil, and thymine in many carbonaceous chondrites. One example of this is in the Murchison meteorite. The Murchison meteorite has been found to have all 5 nucleobases, as well as 70 different amino acids, which are the building blocks of proteins and are essential to life. Furthermore, in 2019, a geochemist found ribose, along with several other chemically similar sugars in 2 different meteorites, which are the NWA 801 and the Murchison. By measuring the amounts of carbon-13, they were able to find out that this sugar has been chemically different from terrestrial counterparts and therefore likely originated from space. Also, in the Allende meteorite, which fell in 1969, there are a diverse array of organic compounds, including amino acids and polyols. While the discovery of organic material in the meteorites is exciting, the transition from these simple organic compounds to complex living organisms is still not fully understood.
Microbiota. So before I start, I'd like to define microbiota. And microbiota are the range of microorganisms that may be commensal, mutualistic, or pathogenic found in and on all multicellular organisms. And so the things that we found in our research regarding microbiota is that the Earth's upper atmosphere collects cometary meteoroids and interplanetary or interstellar dust particles potentially containing organic grains such as bacteria and viruses. Balloon experiments have recovered stratospheric particles, some of which have possible biological origins, indicating the potential presence of an extraterrestrial microbiota. ISRO's 2001 balloon launch collected stratospheric air at 41 kilometers altitude and found both mineral grains aggregates and fluffy carbonaceous aggregates, possibly clumps of bacteria suggesting cometary origin. The presence of microbial fossils and carbonaceous meteorites resembling bacteria and viruses strengthened the notion that life's building blocks have come from space, and distinguishing between indigenous terrestrial microbiota and space origin bacteria remains a challenge, which warrants further research to establish a definitive link and support the concept of panspermia. So our discussion and our conclusion. So throughout our internship and our research, we investigated the different methods by which meteorites could have brought life to Earth. Through the study, we came up with the following conclusions. Microbiota could have survived the journey on meteorites to Earth. Life could have begun outside of our planet. Meteorites carrying life had a high chance of hitting Earth, and there is a clear evidence of microbial ingress of bacteria from meteorites landing on Earth. So SEAS impacted myself and my group in a variety of ways. Participating in the SEAS internship has been a transformative experience that has shaped our team's academic and professional journey. Throughout the internship, our team was exposed to the rigors of scientific investigation and gained hands-on experience in conducting experiments, analyzing data, and collaborating with esteemed researchers. The opportunity to work with experts in the field and listen to their talks has helped broaden our understanding in the meteorites field. Furthermore, we were exposed to a strict grading system that not only helped better our academic writing skills, but also prepared us for a future as a professional in any field. Overall, we hope to use the skills and lessons we learned throughout this internship to pursue a career in space. So I'd like to make some quick acknowledgments on the behalf of my group. We would like to thank Margaret Baggio, Selena Miller at the University of Texas at Austin Center for Space Research, Suzanne Foxworth and Maritza Montoya, as well as all the NASA Aries speakers and all the C speakers for their incredible contribution to our internship and our project and our research. And I'd just like to thank these individuals and these organizations for how much they have helped us.
This is our poster, which we will be submitting to AGU. Thank you so much for listening, and we hope you have a great day.
Congratulations on doing such a great job. We invite teams 3 and 4 to please turn on their cameras and unmute their mics. We have several questions for your group. Team number 3, what were the benefits of using Google Scholar for research?
Sure, I can take that one. So Google Scholar is a very reputable, accessible, and free resource that can be found in a simple Google search, and it gave us access to a vast range of books, scholarly articles, and conference papers from all types of different universities. And also, I was able to find many different data sets that gave us the isotope and noble gas ratios that we were able to compare for our research.
What method is best for identifying meteorites?
What we found in our research was that reviewing the meteorites' volatile signatures was one of the best ways for identifying meteorites or matching them. One example of this was when we found out about the researchers using the xenon isotopic ratio in the Murray and Murchison meteorites. That helped a lot in identifying and matching them.
And also for team 3, did you have an interest in meteorites or geology prior to this internship? What was the most interesting takeaway after your research?
For this question, I would say that this internship definitely spiked an interest and intellectual curiosity in meteorites a lot more for me. And I feel like I know a lot more about meteorites beyond the surface level, like where they can be found and their different subcategories. So I definitely think that it left me knowing more than I have before. And my biggest takeaway on my research on meteorites is how we incorporated different techniques like gas spectrometry and mass spectrometry to distinguish more than 50 monocarboxylic acids within the Murchison meteorite, and how we found that the formic acid was one of the most abundant within that. And this highlighted the significance of how organic compounds were essential to the origins of terrestrial bodies.
And what would you consider to be the most difficult part of your research or this internship?
I think I can take this one. This was kind of a difficult topic. I think we ran into some of the difficulties in trying to align our research together into an outline that kind of made sense and was kind of more focused on a single goal instead of too spread out. So I think that was one of our main difficulties in this internship.
Okay, and for team number 4, what made you select this topic for your research on meteorites?
So we decided to select this topic only because we all agreed that it was pretty interesting, seeing how all these different possibilities about how life could have been seeded on Earth. And to connect it to meteorites, we eventually just came upon panspermia and random panspermia. So that's probably why we decided to choose this topic.
And also for team 4, what does ISRO stand for?
ISRO stands for the Indian Space Research Organization, which is India's equivalent of NASA.
And did you find anything surprising or unusual in your research?
I can take that one. So I found it really interesting that so many bacteria could survive for so long in outer space, despite all the intense UV radiation.
And what do you consider the most difficult part of working in a virtual environment?
I can take this one. So I think the most difficult part of working in a virtual environment for us, at least, is coordinating with the different time zones and just trying to meet up at different times to get our research done. As well as in the beginning, we did have our own independent research paths, so we did have to meet up in order to come to one conclusion together.
So did you divide your project and do research individually and then come together as a team to combine that research? Or how did that work?
We did research all to, for example, I did more research on the Murchison meteorite and the Allende meteorite and their compositions, whereas Eric focused on the early history of Earth, and Jeevan on panspermia, and Roan on microbiota. And we sort of came together with all these different conclusions in order to strengthen our research all together.
Well, congratulations to all of you. Excellent research. Our next series of presentations are by interns in the Urban Heat Island Study Globe Mission Earth Project. Increase in land surface temperature can have negative impacts on wildlife, our land and water resources, as well as on human health and economic activity. Interns studied this phenomena to add to NASA's scientists' knowledge of the topic. Our thanks to the 2 mentors for their leadership and guidance to the Urban Heat Island interns this year. The first Urban Heat Island project will be projecting urban heat island exposure in Texas using socio-demographic factors.
Hi, our research is projecting urban heat island exposure in Texas using socio-demographic factors by Grace Sang and Manat Alwalia.
So here's our abstract describing our research.
To introduce our topic, the urban heat island effect is a phenomenon where temperatures increase due to city infrastructure re-emitting the sun's heat. The objective of this project is to determine whether there is a spatial relationship or possible correlation between demographic factors, specifically income and minority groups present, and the urban heat islands. This will enable scientists to target specific counties that we looked into within the Austin, Houston cities to facilitate the development of more equitable environmental policies. So the 2 research questions that we looked into are certain demographic groups in Texas disproportionately affected by urban heat islands? And also, what is the spatial relationship between demographic factors and the urban heat island effect in Austin and Houston?
So our study area within Texas consisted of Houston and Austin because these areas have historically been affected by redlining and also the current present day residential segregation that occurs in these areas.
So for our research, all the data we used was secondary data. For surface data used in our model, we used the Google Global Surf Urban Heat Island Explorer app. And from there, we extracted data from 38 urban clusters across Texas. For the demographic used in our model, we used the US Census and extracted the data by county. And constructing our maps in ArcGIS, we used two datasets, a census dataset and an urban heat island dataset.
Our data processing techniques began with a spatial component, which essentially used ArcGIS to merge datasets containing the urban heat island effect, as well as different demographic factors. And we used this to create a bivariate choropleth map that analyzes spatial correlations. Our second component, which was the computational part, was first using Excel to calculate the Spearman correlation coefficient analysis with the urban heat island effect versus each demographic factor. From this data, we constructed a random forest model, which is a type of machine learning model that uses ensemble architecture, and it uses multiple different algorithms in order to train and test a dataset. We also repeated testing our model 3 trials in order to determine how accurate it was.
So this is the first map made on ArcGIS, comparing the median household income to temperature. So looking at the legend, the two most significant features to focus on are the bright blue, which signifies areas with the highest temperature and the lowest income, and the dark brown, which is areas with the highest temperature and highest income. The center brown color indicates there's a possibility of little to no correlation. So looking at the Austin map, there is a high presence of the center brown color in the legend, meaning that there's less of a correlation between income and surface temperature. However, in Houston, it is visible that there is a greater correlation. Towards the bottom left of the colored area, it shows that there is high temperature and low income relationship in the southwest part of Harris County and the northern part of Fort Bend County. Next, looking at the percent of minority maps, we're looking for areas where there was high surface temperatures and high percentage of minorities present. So in this case, this is where the dark brown and dark orange tones are present on the map. Again, in Austin, there's less correlation. However, there are some present in central Travis County. In Houston, there is some brown tones present or outside of central Houston, and mainly southwest again of Harris County.
So our predictive modeling used a random forest model, and we trained and tested the dataset using the SUHI intensity from a Yale dataset that consisted of pixel level composites of daytime annual urban heat island effects calculated through this equation. And our model itself involved different decision trees as shown in this image, and we used 100 decision trees to train our dataset of 38 counties across Texas. So here is a sample of our code. We also calculated Spearman rank correlation analyses to determine the R values that would show the correlation. So -1 would show a strong negative correlation and 1 would show a strong positive correlation. And the only R value that was significant was between daytime urban heat island effect and percent black, with an R value of 0.337, and the p-value was less than 0.05. The random forest feature importance also confirmed this, with the greatest feature importance being the percent black versus percent white and median household income. We also trained and tested the model to determine accuracy with an 82% mean accuracy and 84% on the highest performing trial. However, one limitation is that our small sample size of only 38 different counties could have skewed the accuracy in some way. So in conclusion, we have determined a significant correlation between urban heat island effects and the percent of Black people residing within one county, which could be an effect of redlining within the 1950s, and this could cause segregated neighborhoods that have less capital and less resources to construct areas that have less impervious surfaces. And the results indicated no significant correlation with the median income or percent of white data sets. However, in our spatial analysis for Austin and Houston, we determined there could be a possible relationship between urban heat island effect and demographic factors in Travis and Harris County, and we also predicted the urban heat island effect with demographic data with an accuracy of up to 84%.
Some of the best features of this research was we were able to experiment with machine learning models and using new programs and softwares, also learning how to collect real-world globe data. Some challenges we face is we originally tried to create our maps on Google Earth Engine, but we had trouble merging our data sets. We also had to complete this in a short amount of time, and there was a learning curve for ArcGIS and Google Earth Engine.
So from this internship, I've gained a lot of experience with research and conducting my own projects. And I've also realized and fine-tuned my future career path that I'd like to go into, which is data science.
This internship has given me the experience to conduct real-world research and learn about the opportunity available through remote sensing and data analyzing.
So thank you to our mentors, Femi, Tanzia, Dr. C, and Dr. Yitong for their support throughout this internship. We'd also like to thank the NASA STEM internship itself for providing us with these opportunities.
We have learned a lot of valuable information about data analysis and the urban heat island effect. Thank you.
Great research. So our next presentation will be the Urban Heat Island Impact Modeling on Groundwater project.
Hi, my name is Allie.
Hello, my name is Ian.
And for our project, we studied the correlation between the urban heat island effect and Los Angeles groundwater depth. For some context, 30 to 60% of California's groundwater, sorry, 1 second. Can you go back?
Yeah.
I said groundwater supply, but it's water supply. Okay. So, hi, I'm Allie.
Hello, my name is Ian.
And for our project, we studied the correlation between the urban heat island effect and Los Angeles groundwater depth. For context, 30 to 60% of California's water supply comes from groundwater, and we rely on it particularly during its dry years. Some definitions related to our study you'll need to understand are, firstly, an urban heat island refers to a localized and significant increase in temperature within an urban area compared to its surrounding rural or natural environments due to human presence and human activity. These areas of increased heat and rapid urbanization subsequently create subsurface urban heat islands, which are caused by impervious and low albedo surfaces like concrete and asphalt and lead to increased temperatures, which warm the ground and particularly affect aquifers, which are rocks that contain groundwater. Additionally, a thing that you'll need to understand is that a water table is the upper surface of the groundwater in an unconfined or shallow aquifer, which is what our study references. So knowing that urban heat islands lead to subsurface urban heat islands, which ultimately create temperature anomalies in shallow aquifers, we attempt to answer these two research questions. One, how have the temperature anomalies changed groundwater table height? And two, how does geography affect water table height? So here are areas of interest. This is Los Angeles County, and we mainly examined districts 3, 2, and 4. Here is the geographical location of our digital elevation model that you'll see in the next slide. It's a 3D rendering of part of Earth for context, and it helps us to understand our study area better. Here is our geographical context. As you can see, Los Angeles is filled with mountain ranges and valleys, which is important in the context of groundwater interpolation and analyzation. So as for our data mining and sourcing, we used various different shapefiles, CSV files, and Excel files sourced from many groundwater subrepositories and repositories. That was just for context, but as for our methodology, first we visualized urban heat island extent comparing daily temperature data. We layered that data onto LA County in QGIS, and we created aftermap after 2000 of water table depth, and we interpolated that data. And we examined the discrepancies finally in Sigma plot.
So a lot of our data analysis was done through these programs of QGIS, SigmaPlot, NOAA, and ArcGIS Online. And this is just a very brief overview of some screenshots that I took while doing the data analysis. So to go over our figures now, the first figure that we see displayed here is a display of temperature data
over a 1-year period from 1950 and 2023. From the naked eye, this doesn't look like much of a discrepancy, but when we look at the attribute tables of these plots, we can see that there's an almost 3 degrees Celsius discrepancy between 2023 and 1950, which is a considerable amount. And then I created these plots in Sigma plot, which show that as time goes on, temperature also goes on. And if you look at the temperature data, we can also relate it to the water table depth, and we can see that there is a positive relationship between all 4 variables. Positive correlation, I should say. And with that correlation, I mapped the water table depth onto a QGIS base map, and then interpolated it using IWD interpolation. And we can see that the areas of red are the places with the deepest water table height. And qualitatively, if we examine that and compare it to DAM model on the right, which has shape files of every single building outline in Los Angeles, we can qualitatively see that the areas of deepest water table depth is also the areas of greatest urbanization in Los Angeles. Now, to put all of these variables together, we visualize the data in Sigma plot using a 3D mesh graph. And in the 2D plane on the XY, we can see a relationship between time and temperature, which is positive. And then I took time temperature versus water table depth, which also shows a positive trend as it goes up on the diagonal. And now so far it's all been correlation, but to try to dispel that the discrepancy between correlation and causation, and to make sure that there is the most amount of causation, assuming possible, between water table depth and urban heat, we created another table where we examined the relationship between not temperature, but precipitation. We could intuitively kind of guess that if there was more precipitation, we would assume that there would be a shallower water table height. But if we graph that relationship, we can see that's actually not the case. So we know that precipitation is an invalid variable, and that it's more likely to be the cause of temperature and urban heat that affects water table depth.
As for our conclusions, we had 4 main takeaways. 1, the urban heat island effect, urbanization, and increased temperatures is not correlation but causation. 2, at any particular groundwater well study site, depth till water table increased as a function of temperature. 3, the areas of most distance till water table were in areas of the greatest urban density. And after examining various variables of precipitation, temperature, water table depth, and the relationship between urban heat islands and groundwater depth, we have determined that the relationship is not correlation, but causation.
Thank you.
Thanks for listening.
Our next urban heat island team researched the urban heat island effects on agricultural land.
Hello, my name is Naisha Jane, and I'm from Capel, Texas.
Hi, my name is Claire Nikes, and I'm from Pasquo-Sham, Mississippi. Nyasha and I are on the 2023 NASA SEA's Urban Heat Island team. And our research topic this year was on how the urban heat island affects agriculture land. So some background on our topic. We chose to examine the correlation between agriculture and urban heat island because of how important agriculture is to society. It provides us with food, clothing, and is also an important economic factor for the United States. So some terms we will be using is the urban heat island effect, which is a scientific theory that cities withhold more heat than their surrounding rural areas due to the lack of vegetation growth, which occurs because of modern buildings and other infrastructure. We will also be using the normalized difference vegetation index, which we will refer to as the NDVI, and the land surface temperature as LST to better understand the urban heat island effect. So our research goals were to determine how the urban heat island effect impacts the vegetation of its surrounding rather than observing the vegetation within the city. So instead of trying to prove what was happening to the vegetation within the cities, we wanted to look outside the boundaries of the cities into the rural surrounding areas to best observe the urban heat island impact. So based on our topic goals, we formulated 2 research questions. The first is, what is the correlation between the urban heat island effect in Salem and Portland and vegetation cover in Willamette Valley, Oregon? And the second, over the past few decades, how has the urban heat island effect in Salem, Oregon influenced the surface temperature of Willamette Valley? To find the most accurate answers to our research questions, we wanted to find an area that had agriculture land surrounding large cities. So for our study area, we chose Oregon for its rich farmlands and forestry, and also its largely populated cities. Within Oregon, we specifically looked at the cities of Salem and Portland, which are both surrounded by the Oregon Willamette Valley. And our time frame for our study was 1 to 2 decades during the summer season, so during the months of June, July, and August.
We primarily use Google Earth Engine, specifically datasets from Landsat 8 and 9, to collect both quantitative and qualitative data for Salem, Portland, and the Willamette Valley. Additionally, we use datasets from USGS, ArcGIS, and GLOBE to support our findings. On to our first research question, which essentially observes the correlation between the LST of 2 cities and NDVI of the valley. This data table holds all of the summer monthly averages for LST and NDVI for these 3 locations, and this data came from Google Earth Engine. This graph illustrates the NDVI versus LST for these 3 locations. There appears to be a slight positive correlation between these variables in Salem and Portland. However, in the Willamette Valley, there appears to be a constant relationship between the variables as its trend line is horizontal. Statistically speaking, we use the Spearman correlation, which ranges from -1 to 1, where the endpoints indicate strong correlation between the 2 variables and 0 means no correlation. When assessing the LST and NDVI correlations in all 3 locations, we found that the correlation was 0.248 in Salem, which indicates a weak positive correlation. In Portland, the correlation was 0.329, which indicates a moderate positive correlation. Finally, in the Willamette Valley, the correlation was 0.002, which indicates hardly any correlation. To visually demonstrate this correlation, we extracted a geospatial map from the Willamette Valley's summer season in 2016. In the western part of the LST map, the area appears to be 50 degrees Celsius. In the southern large plane of the same map, the area appears to be around 40 degrees Celsius. On the left-hand side NDVI map, both of these regions appear to have similar, close to 0 NDVI values, regardless of the LST values. This illustrates how the LST and NDVI values are not influencing one another to a great extent. To take our research one step further, we also observed both of these variables over time. Starting off with the NDVI graph here, we can see that for the majority of the years, the NDVI was the greatest during the month of June. These NDVI values tended to exceed 0.6, which indicates dense vegetation. After June, over the past decades, the NDVI values typically declined over the next summer months. This graph illustrates the LST values of all 3 locations over time. Typically, the LST values were the greatest in Salem among the data we collected. This is surprising because Portland is more urbanized with skyscrapers and more infrastructure in comparison to Salem. Thus, intuitively, based on the urban heat island effect, we would assume that Portland would have the greater LST values. However, our findings appear to contradict this idea. Our final graph illustrates both variables over time. As depicted in these gray regions, in the past, the NDVI had longer spans of direct relationships with the LST values. As we progress towards modern day, this direct relationship has become weaker.
So for question number 2, we looked at how the LST of Salem was specifically influencing the LST of Willamette Valley. This slide shows the specific correlation of the LST in Salem compared to that of the Willamette Valley. Only left is the surface temperature for both Solemn and Wilmette Valley during the summer months, ranging from the years 2000 to 2020 in 5-year intervals. On the right is a clearer visualization chart of this same data. From this, we can see that the LST of Solemn has a much greater fluctuation of temperature than its surrounding Wilmette Valley. We can also see that while Solemn's changes appear to be extreme, Wilmette Valley's remain steady, with a slight increase over the years. From the current theory of UHI, we would have assumed that this would not have been the case, and this data came from NOAA and the Landsat satellites. To further understand this data, we use Landsat imagery. This images on the top show the area of Solemn specifically, whereas the images on the bottom show the area of the whole Wilmette Valley. You can see from these images that there is clearly a gradual increase of LST for both Solemn and the Wilmette Valley, but we cannot prove that this is due to the UHI of Solemn because there does not seem to be a direct correlation between the two from the data or images. And here we have data from GLOBE, with Solemn on the right and Wilmette Valley on the left. This further shows a natural increase in temperature for both, but Wilmette Valley's does not appear to be as significantly influenced by Solemn. Thus, this further proves that there does not appear to be a direct correlation between Solemn and the Wilmette Valley, which is not what we were originally expecting based on the UHI theory.
We have concluded that there is a weak to moderate correlation between the LST and NDVI between the cities of Salem and Portland and the Wilmette Valley. Additionally, the LST values were very similar in Salem and Wilmette Valley as a whole. We have two more conclusions that we have listed on this slide. Here are our group's opinions on the NASA SEAS internship experience. Personally, the SEAS program boosted my passion for geospatial research and learning new softwares, regardless of the learning curves. Thus, I'm excited to continue researching and providing findings to the scientific community as a part of my future career.
Similar to Nyasha, the SEAS program gave me the opportunity to learn more about the Earth data that is currently available and the different technologies and programs scientists use. I hope to attend college next year for computer science and research more ways that technology can be used to help farmers and the public. And we would like to take a moment and thank our team and all those who have supported us and our progress this summer.
Excellent job. So we have several questions to groups 4, 2, and 3. So we invite you to please turn on your cameras and unmute your microphones. Our first group of questions are for Team 4, Grace and Manet. Was it easy or difficult to use the UHI app?
So for the UHI app, are you talking about like the Globe app?
Yes.
Yeah, so originally I did have some like complications with using it and with providing my own data as a resource, but afterward, after watching some tutorials, I think I mostly got the hang of it. And also our research was mostly based on like secondary data, so I think we didn't use the Globe app as much as other resources.
And another question for your team is, why did you select ArcGIS for your data?
We selected ArcGIS because it was easier to find the data sets to merge census data, which worked by county, and temperature data. We originally tried to do this on Google Earth Engine, but the code was harder to create, so we used ArcGIS.
Why do you think there is such a discrepancy between Austin and Houston's data with your data relationship?
I can take this question. So between Austin and Houston, I would say that from our prior research as well, we found Houston to have like greater residential segregation in general compared to Austin. So I would say that would definitely have a difference in the discrepancies between like the percentage of minorities as income groups that have a relationship with urban heat island effects.
And how did you overcome those challenges with data sets? Anyone want to take that one? Okay, we'll move on to team. Go ahead.
We chose data sets from 38 clusters that had sufficient data within the Texas area, and it was more sufficient data in Houston.
Okay, great. So we're going to move on to team number 2, Alexandra and Ian. Did you have any personal connection when selecting your research topic?
Yeah, we're both California residents, and California is prone to periodic droughts. So we both lived through many, and during dry spells, surface water becomes scarce and reliance on groundwater increases. So we've been firsthand witnesses to the ways in which we rely on our groundwater resources and why it's important that we manage them well.
Did you find anything surprising while you were doing your research?
Well, one thing is that Los Angeles has actually a pretty big mountain range to the northeast. So one thing we found surprising is that because of that mountain range, the calculations for well sites were really skewed in that the way we calculated was from surface of the soil to the water table. And because of the mountain range, those data were incredibly skewed upwards. So we had to account for that and delete the height of the mountain ranges in our calculations.
What did you find was the most difficult part of working on a virtual internship?
We actually worked very well together because we are on the same time zone, but coordinating was difficult. It was useful, though, that we were working on online platforms where it was easy to share our data. We use QGIS, so it was easy to share our base maps and our data sets through there. So it worked out well for us, I would say, but in general, the communication did prove to be a little challenging.
Okay, so for team number 3, what were factors that made you select your topic?
So both of us were interested in agriculture and seeing how the urban heat island effect would impact the productivity of the surrounding lands. So that's why we chose this topic.
Why do you think there is a constraint correlation in Willamette Valley? And this is for team 3, Naisha.
Sorry, can you repeat that?
The question was, why do you think there is a constraint correlation in Willamette Valley?
I didn't hear the question.
So maybe just explain to us why do you think there is a constant correlation in Willamette Valley?
The constant correlation at Willamette Valley is primarily Nyasha, do you want to answer this? I'm having microphone problems. Nyasha, do you want problems?
Yes, I can answer it. So we thought there was a constant relationship because when we graphed it on a line graph, the trend line was horizontal and the Spearman correlation appeared to have no correlation. So rather, we thought there was a direct relationship than correlation between the variables.
Great, thank you. Did you find your research, and this is for any team, on urban heat island interesting? And would you want to continue in this field of study? What did you find that surprised you the most? This is for any team.
So I found our research really interesting because the temperature in Salem was higher than Portland. So that was kind of contrary to what we believed the urban heat island effect would tell us. And so I think I would want to continue this sort of research in the future and maybe even add on to this research.
And then we also have one more question for your team. Do you have a hypothesis as to why Portland's LST values were less than Salem?
Yes, because the urban heat island effect isn't just applied based off of urbanization. It's also affected by geographical factors. And in Portland, there was a river which could have reduced the land surface temperatures in the city.
Do you think the difference in total area and land cover of city and same of the valley has an impact on the difference in LST?
Yes, I think so, because it is the urban heat island effect is impacted by the geographical area as well.
Great. Well, you've all done an excellent job and we appreciate you sharing your research today. The next urban heat island team will be exploring the urban heat island effect through humidity.
Hi, so this is the top of our project. It is the damp cityscape exploring the urban heat island effect through humidity by Kennedy and Daniel. I'm Danny. You ever notice the heap of steam that lingers after a hot shower and keeps the bathroom warm even after the shower is over? Well, turns out that the tiny droplets that create humidity can hold on to heat. So as we explore the urban heat island effect and its effects on temperature, we cannot neglect the role of another key heat determinant, which is humidity. That's what our case study is on. So we chose our location as Central Florida because Central Florida is a key and notoriously humid environment, as long as and it also has a very urban environment as well. So it's a great combination for our case study, which is to study humidity and its effect on the urban heat island effect. So I'm going to pass it on to Kennedy.
That being said, our study aims at answering the following two questions. How have humidity levels within the urban areas changed over the last decade, and how has it affected the urban heat island effect? The time frame will be between 2012 and 2022, and I will be in charge of answering this question. My partner Daniel will answer how does soil moisture affect humidity levels, and how does this affect the urban heat island effect. His time frame is between 2015 and 2023. In terms of background information, one crucial study we found told us that there's a negative correlation between relative humidity and urban heat island intensity. In other words, as relative humidity increases, the urban heat island intensity weakens. The scatter plot depicted here actually reveals that larger magnitudes of urban heat island intensity occur during conditions of high relative humidity, while the highest urban heat island intensity occurred during hot afternoons when the air was much less humid. A second source we analyzed told us that the urban heat island effect can be explained by changes in the efficiency of convection, which in other words is the transferring of heat between land surface and atmosphere, which, funnily enough, humidity can help conduct through water vapor. And essentially this implies that humidity can help us suppress the urban heat island effect as it allows for convection to actually occur. Finally, a third source we looked at explained that there's a synergistic relationship between urban heat island and urban moisture island, which, similar to urban heat island, is related to moisture and implies that higher moisture levels are found in areas of higher vegetations or usually are more rural areas. And it explains that although plants do help with the urban heat island effect by allowing for convection to happen through water vapor and evapotranspiration and other plant processes, it does increase the urban moisture island as a result. In terms of what we did to conduct this study. I sourced my data from Florida Climate Center's monthly climate reports, specifically for my air temperature data, and sourced my humidity data from Weather on the Ground's monthly reports. I then took this data and calculated monthly averages in Google Sheets and created an ArcGIS slider map using this data showing the last 10 years. Then I created a time series graph and regression graph for both relative humidity and temperature. And finally, my partner Daniel made use of SMAP data to create regression graphs comparing soil moisture and humidity, soil moisture and land surface temperature, humidity and land surface temperature, and finally, a Google Earth Engine layered map to depict all of these data sets. It's also important to note that he sourced both the land surface temperature data from Landsat satellite data on Google Earth Engine, as well as humidity data from Google Earth Engine. Moving on to my analysis, as you can see on the left, this is the average relative humidity over the last 10 years, and it does seem to be fluctuating a lot, but seems to be on somewhat of a decline since 2017. It oddly peaked at 89% in June of 2017, which could be explained by some sort of climate event that occurred in Orlando, Florida. However, it is important to note that drier air usually means higher temperatures, as we've established, so the expectation is for there to be higher temperatures around this time as well. And that is somewhat what we see. Overall, temperature seems to stay pretty consistent. It stays above 75 degrees Fahrenheit, and actually peaked in July 2016, around the same time that relative humidity peaked, which is certainly a good sign. And it has been slowly increasing, very slowly, since June of 2017, which does support the relationship we established earlier. Moving on to my time series graphs and regression graphs, as you can see on the left, here is my regression graph comparing the average temperature and relative humidity, and the trend line seems to be steadily going down, which I did not expect. It basically goes against everything we learned up until this point. And it pretty much shows us that as relative humidity increases, the temperature actually decreases. That being said, we should consider that the R2 value is 0.278, and to clarify, the R2 value tells us the reliability or the strength of the trend line in showing us the relationship between both data sets. And given that it's a scale between 0 and 1, the reliability of this trend line isn't very high. Moving on to my time series graph, as you can see in the boxed area, we get an exact point that explicitly shows us a point where average temperature was increasing and relative humidity was decreasing, and later on, relative humidity was increasing while average temperature was decreasing, which again supports the relationship we established before. It is important to note that given that temperature has stayed pretty consistent across all 10 years, it kind of seems like it's indifferent to humidity, almost like it doesn't really care about it, isn't really affected by it, which does put into question what we know. Finally, here are the slider map visuals that I created. As you can see on the upper one, overall the humidity levels seem to be decreasing since 2017, as established earlier, while temperature has been gradually increasing. But prior to then, temperature was steadily increasing, but hit a plateau in 2016. And after that, there was a large spike, and then decreases to a more reasonable amount, thank God. And since then, humidity has been mildly random until 2017. And most importantly, if you view both maps in relation to each other, you can see that at the start, humidity always seems to be smaller than temperature, which does help enforce the relationship we have established, and all the other data sets and graphs and observations we made previously.
So to start off, here's some map layer visuals. You can see the soil moisture, the humidity, the land surface temperature on Google Earth Engine. So here is my data on what happened. So it shows that everything's kind of linear, and you expect the graph to actually just fluctuate, but it doesn't, because it's a linear regression. So everything kind of impacts each other. If the soil moisture goes up, then the humidity goes up. If the land surface temperature goes up, then the humidity goes down. As a result, the soil moisture goes down. So you would expect everything to fluctuate, but it doesn't, because if everything remains linear, then everything else remains linear as well. And this is backed up by the time series graph that I'll be showing you right now. As you can see, the land surface temperature fluctuates from a time series. This is due because of that the land surface temperature actually depends on the season, because everything correlates to each other. For example, if it was a cold season, then that means the land surface temperature will go down, increasing and if you look at the graph, that means the overall temperature for soil moisture and humidity will go up and raise. However, the land surface temperature and humidity are inversely proportional, just like a math equation. That is why it fluctuates in this time series chart. It just keeps going up and down because it depends on what season it is. So here are our resources, and thank you for listening.
Our next presentation is from the Urban Heat Island team, Soil Moisture and Urban Heat Island Effect.
Soil moisture and the urban heat island effect. This was prepared by me, Mariama, and my research partner, Pranita, under the guidance of our mentors, Mr. Femi and Dr. C.
Starting off with our introduction, the urban heat island effect is when temperatures in urban areas are higher than the temperatures in surrounding rural areas. However, not all cities are affected in the same way. Coastal cities can have a moderated urban heat island effect because coastal water bodies may cool surface temperatures. Inland cities, on the other hand, may experience larger daytime temperature variations as a result of the urban heat island effect, because the lack of water bodies in inland cities can serve to intensify heat retention. Soil moisture is something that may be impacted by the urban heat island effect. Soil moisture is the amount of water held in the spaces between soil particles. As the urban heat island effect raises the temperatures in cities, evapotranspiration rates also increase, which leads to a decrease in soil moisture.
Our research study is focusing on two questions. For our first question, we're going to compare the soil moisture and surface temperature in a coastal city, Toledo, and an inland city, Bowling Green, to determine if there is a difference in soil moisture. And for our second question, we will look at the soil moisture from an inland city in two different sample locations, one in an area with vegetation and one in an area without vegetation, to determine if there is a difference in soil moisture in those locations.
Our hypothesis for our first research question is that the soil moisture in the coastal city, Toledo, will be higher than the soil moisture in the inland city, Bowling Green. We are assuming that the water body near Toledo will have a cooling effect on the surface temperatures and thereby increase the soil moisture. Our hypothesis for the second research question is that the sample location in Bowling Green with vegetation cover will have more soil moisture than the area without vegetation cover.
This is a map of our coastal city, Toledo, Ohio. Toledo is located near the western Lake Erie Basin.
This is a map of our inland city, Bowling Green, Ohio.
For our methodology, we are using data collected by the SMAP, or Soil Moisture Active Passive Satellite, which we access through the GLOBE database. The gravimetric soil moisture in Toledo, Ohio will be collected from February through April of 2017 and 2018, while the gravimetric soil moisture in Bowling Green, Ohio from September through November in 2017 and 2018.
As we mentioned previously, this study will also look at the gravimetric soil moisture at 2 different study sites in Bowling Green, Ohio from 2017. The first sample site will be soil taken from near a parking lot, which does not have vegetation, and the second sample site will be soil taken from an agricultural field, which does have vegetation. This data will then be graphed, and a t-test will be used to determine if the difference between the soil moisture and the different locations is statistically significant.
This graph is showing the gravimetric soil moisture at the University of Toledo from 2017 to 2018 in the months of February through April. The highest recorded soil moisture was 0.34.
This graph is showing the surface temperature data at the University of Toledo from 2017 to 2018.
This graph is showing the gravimetric soil moisture at Bowling Green University from 2017 to 2018 in the months of September through November. The highest recorded soil moisture was 0.38.
And this graph is showing the surface temperature data at Bowling Green University from 2017 to 2018.
This graph is comparing the average gravimetric soil moisture content at the University of Toledo and Bowling Green University from 2017 to 2018. The average for Toledo was 0.1765, and it was less than the average for Bowling Green, which was 0.2114.
When we conducted a t-test, we received a p-value of 0.014. Since this is less than 0.05, it indicates that there is a statistically significant difference between the gravimetric soil moisture content in a coastal city, Toledo, as compared to an inland city, Bowling Green.
We noticed that the surface temperatures at Bowling Green, Ohio, were typically higher than the surface temperatures at Toledo, Ohio, despite the fact that surface temperatures at Bowling Green were taken during autumn months, from September through November, while the surface temperatures at Toledo were taken in spring months, late February through April. Although spring is typically characterized as being warmer than autumn, Toledo's cold spring could be a result of the cooling effect Lake Erie has on surface temperatures.
Higher temperatures lead to higher rates of evapotranspiration, which is supposed to decrease soil moisture. However, the soil moisture at Bowling Green is higher than the soil moisture at Toledo, despite the temperature being higher at Bowling Green. This could be because the average surface temperature at which soil begins to lose moisture is around 30 to 40 degrees Celsius, and the highest average temperature at Bowling Green was during November of 2017, with 26.19 degrees Celsius. Therefore, soil moisture likely did not decrease at Bowling Green because temperatures were not high enough for the soil to lose moisture.
Now we are looking at our second research question. In this graph, we are comparing the average gravimetric soil moisture in an area without vegetation coverage, which is a soil located near a parking lot, and an area with vegetation coverage, which is the soil taken from an agricultural field. The soil from near a parking lot has less soil moisture than the soil that was taken from an agricultural field.
When we conducted a t-test, we received a p-value of 0.023. Since this is less than 0.05, it indicates that the difference between the gravimetric soil moisture in an area without vegetation and an area with vegetation is statistically significant.
The soil moisture sample taken from an agricultural field was higher than the soil moisture in the sample taken near a parking lot. This result was expected because the agricultural field had vegetation, and soil moisture is higher in areas with vegetation, as the roots of plants help to hold water in the soil, which prevents water from evaporating as quickly.
Here are a few of our references that we used for this project.
One of the challenges that we faced while conducting this project was that we were unable to find soil moisture data for certain locations, such as Madison, Wisconsin, or certain time periods, such as specific months, from the GLOBE dataset. Another challenge was the short amount of time that we had to come up with a research question and prepare a presentation about it. One of the best features of this internship included being able to conduct our own research about a topic that we were curious about. Another was learning how to access the Globe database and being able to create an interactive project on ArcGIS.
We would like to thank our C's mentors, Mr. Femi and Dr. C, for all of the help they gave us in coming up with our research question and determining the best ways to go about collecting our data. We would also like to thank the C's program for giving us the opportunity to spend our summer learning from this internship. Thank you so much for listening to our presentation.
Great job. So we would like all members of the two teams to please turn on their cameras and unmute their mics. We have several questions. The first question is for team number 1. How do you think your information can influence current studies?
Well, I think that our current information can influence different studies because as we come to understand more how humidity affects the urban heat island effect, we will soon learn how to diminish it and sort of lower it so it can help future societies, and it won't destroy our environment even more, causing our destruction of humanity.
You have a hypothesis as to why there was a decrease in your graph that might have surprised you.
Well, that was Kennedy's question, sorry, but she's not here today, so I'm gonna take what
I think she just joined.
Oh, she just
Kennedy?
joined? Okay.
I hypothesized that it was due to some sort of climate event at the time that took place in Florida, because it was like a huge outlier compared to all the other data sets that we had collected. And that's in reference to the increase.
Mm-hmm. Okay, and for team number 5, what made you choose your sample locations?
I can answer this one. We chose Toledo and Bowling Green because they had the most data available for us for soil moisture.
Mm-hmm. Did you find working on and collecting UHI research interesting? What was the most interesting thing that you learned?
I found working with UHI data is extremely interesting. You know, I live in Madison, which is kind of an urban area, and it was just interesting to see like the data like right in my face, and you know, being like, okay, so this is why it's so hot today, but then in Mount Horeb, like in the village, it's like cooler. And yeah, what was the second part of the question?
What was the most interesting thing that you learned?
Oh, yeah, I think the most interesting thing that I learned while conducting my research was that the soil moisture in Bowling Green was actually higher than the soil moisture in Toledo. That was really surprising because I thought that the soil moisture in Bowling Green would be lower because it's inland and Toledo is like on the coast. So I thought that was really interesting.
Hey, and then for anyone who would like to answer, did your C's internship influence you in any way about your future career path?
Not really, but it opened me up to thinking about more about research and how important research is.
Well, thank you all for your research. Your projects seemed really interesting. The success of the NASA STEM Enhancement in Earth Science program is determined not only by the commitment and research by student interns, but also by their mentors and project assistants. Your passion for youth development, STEM learning, and NASA opportunities is to be applauded. Selena and I want to thank you for your time and the talent that you shared with the student interns. I know the C's interns appreciate your guidance and advice as they conducted their research. We also want to give a special thank you to Angelica Kurizinga, the CSR Communications Coordinator, for her hard work and effort throughout the SEAS internship. SEAS 2023 has provided high school students from across the nation the opportunity to engage with NASA subject matter experts, conduct authentic research, and share their projects and research with each of you. We are excited to see what the future holds for these stellar students, our future scientists and engineers. Congratulations to all the NASA STEM Enhancement in Earth Science high school interns. This concludes the 2023 SEAS Science Symposium, and we thank each of you for joining us.